Welcome to this course where we will talk about recursion. To introduce this course, I want to talk about a game that you probably played before, the Tower of Hanoi game. We have n disks and 3 packs A, B and C, and the goal is to take those n disks from A to C, knowing that you can take one disk at a time and you cannot put a small disk on a big one. A represents the source pack, B represents the auxiliary pack, and C represents the destination pack. What if I tell you that given any amount of disks, we can get the steps to follow to win this game by using recursion? For example, if 1 is equal to 4, this is what we get. But before talking about it, let's first see what does recursion mean. A very important element in programming is the function, a block of code that eventually receives input, performs some instructions, and eventually returns an output. And a function can call other function, it's totally normal, but what if it calls itself? A function that calls itself is called a recursive function, and this is what recursion about, is the action of defining a function that calls itself. By following our intuition, we may think that the function will call itself again and again infinitely. You have to know that a recursive function has a condition where it stops. It's called the base case, we will talk more about it later. Now we go back to our Tower of Hanoi game. We want to move n disks from source to destination, and in order to do that, what we can do is that we move n-1 disks from source to auxiliary, we move 1 disk from source to destination, and we move n-1 disk from auxiliary to destination. And you can notice that inside the process of our move disk action, we are using the same action, which is to move disks. I know that it sounds weird, counterintuitive and all what you want, but after this course you'll become familiar with this idea, you will understand why do we need it, how does it work, how to use it, and many other things. If we follow our intuition, we may think that this process won't stop, because moving n-1 disks will require us to move n-2 disks, and moving n-2 disks will require us to move n-3 disks, and so on infinitely. But no, because after a moment we will reach the case where n is equal to 1, in other words, where we have only 1 disk to move, and in that case we just take it from the source to the destination we want. We don't need to call the same function again, we do it directly, it's what we call a base case. So a recursive function has a recursive case where it calls itself again, and a base case where it doesn't call itself again. It's necessary to stop the process at some point. And what we did here is that we use recursion to keep dividing the original problem, which is to move n disks from the source to the destination, until we arrived at small instances of the same problem, which are to move 1 disk only. I know that you probably didn't understand everything about what we did now, and you have a lot of questions, but don't worry, all of that will be explained in detail in the lectures of this course. Now let's see more examples on recursion. Okay, let's suppose that you have a sorted array of integers and you are searching for the index of a specific value, let's say 6 in this example. And by comparing the search value with the element in the middle, you notice that the search value is smaller, so you deduce that the search value can only be in the left half because all values after the middle are greater than 6. This is why you repeat the same function but on the left half only. You compare with the middle and you notice that the search value is greater now. You deduce that it can only be on the right half. This is why you repeat the same function again but on the right half only. Now you compare with the middle and values are equal, so you finally found the searched value by using the power of recursion, because each time we call the same function but with a different input until we reach the base case where we found the element and we stop there. This searching algorithm is called binary search, by the way, and it works on sorted arrays only. You want another example? It's coming. Let's suppose that you have an array of integers like this one and you want to sort it, but the problem is that you don't know how to sort an array, you just know two things. The first one, you know how to merge two sorted arrays into a sorted one by always comparing the next two elements and taking the smallest until there are no elements left. And you also know that an array that has less than 2 elements is already sorted, so you have nothing to do. If you followed well the first two examples, you'd guess that it's the base case, you'll see why soon. So by combining your knowledge, you decide that instead of sorting the whole array, you split it into 2 parts, you sort the left part, you sort the right part, and you merge them into a sorted array that represents the initial array but sorted. And this is what we want to get. But wait, now you face the same problem again, you don't know how to sort the 2 parts, so you decide to split them into 2 parts. But same problem again, you don't know how to sort all these parts, and what do? Splitting again. And you end up with having to sort these arrays of 1 element, but fortunately you know that they are already sorted, so you reach the base case. And now you have to start merging. So you merge these two, these two, these two, and now you sorted the left part of the original array. Right part now, you join these two, and you got the right part sorted. The last thing to do, you just join these two sorted arrays into one by taking 1, 2, 2, 3, 4, 5, 6, 8, and you get the original array sorted. This sorting algorithm is called merge sort. You can notice that we follow the same principle as the two previous examples. We kept dividing the problem into smaller instances of the same problem that are easier to solve until we reached the base case, and we joined results until we went back to the original function call, recursion. Another example, let's go. You have a file system made of files and directories, where directories can contain files and other directories like this one, and you want to get the total size. Know that the size of a directory is the sum of sizes of files and directories inside it. So in other words, we want to get the size of the main directory. Let's call it the root. And in order to do that, we sum the sizes of all files with sizes of all directories inside the root. Getting the size of a file is easy because it's one of its attributes, but to get the size of a directory, we have to get sizes of what's inside it. This is why this problem has a recursive nature. We have directories inside of directories inside of directories, etc. And to solve this problem, we can use recursion. We keep getting sizes of directories by calling the same function over and over on each subdirectory until we reach the ones that have no subdirectories. You'll see the code in the next lecture. Now I want to talk about an important thing. If you already watched videos on recursion before, then the first examples of recursion you've heard about are probably factorial and Fibonacci sequence. And I didn't want to start the course with them as many other people do, because I consider that those are bad examples to introduce recursion. Let me tell you why. Let's start with factorial. Factorial n is basically the product of all integers from n to 1. For example, 5 factorial is 5 times 4 times 3 times 2 times 1, for instance. And it has a recursive nature because n factorial is n times n minus 1 factorial, and the base case is 1 factorial, which is just 1. So yes, I could introduce recursion with factorial function, and I know that it's easier to understand than Tower of Hanoi and merge sort. But the problem is that if you studied iteration before, which is probably the case, the first reaction would be to ask, why don't we just use a loop? Why would I bother myself using recursion instead of just using a for loop that calculates n factorial? And you'd be totally right, because even if we can show how recursion works with factorial n, you wouldn't get the point of using recursion instead of a simple loop. The second example is even worse, the Fibonacci sequence example. In the Fibonacci example, we want to get the value of the nth term of the Fibonacci sequence, where the nth term is the sum of the two previous terms. We also have the base case where n is smaller than 1, where Fibonacci of n is just n. And you can see that this example also has a recursive nature, because in the recursive case, the fib function is calling itself. But the same problem occurs here. We could easily get the nth term by using a simple for loop, so you wouldn't get the point of using recursion. And there is another problem with this example, its efficiency, because if we have a look at the function calls of Fibonacci 6, for example, we'd find a lot of redundant work, so this implementation will be slow. This means that not only Fibonacci can easily be implemented with a loop, but also iteration doesn't have this redundancy problem. So if I introduce recursion with these two examples, factorial and Fibonacci, you'd probably think that recursion is just an inefficient alternative to iteration, which is definitely not the case, because you'll learn how to optimize a recursive function later in the course. And also, not all problems can easily be solved with a loop. You can easily compute factorial of n and Fibonacci of n iteratively, but try to solve Tower of Hanoi iteratively. Try to implement merge sort iteratively, even if you can do it, but it's way harder than doing it recursively. A little recap, recursion in programming is when a function calls itself, and we can use it to divide a problem into smaller instances of the same problem and solving them by calling the same function over and over until we reach the base case. I know that you have a lot of questions in your head, how to determine the base case, how to write the code of a recursive function, what exactly happens when calling a recursive function, and so on. But don't worry, we'll be answering them in the next lectures. See you in the next one. Before moving to the next lecture, please go check the description of this video. You'll find resources of this course and links to other courses that you can check if you like this one. Welcome back to the course. In this lecture, I'm gonna answer two questions: how to write a recursive function and what happens when a recursive function is executed. Let's start with the first one. A recursive function requires only two things: a function call to the same function and a base case to stop the recursion at some point. But things can become complex because we can have multiple base cases, multiple recursive cases, multiple function calls, some code before the function call, some code after the function call, etc. So writing a recursive function requires a good understanding of what happens in the execution, and that's what we're gonna see in the second part of this lecture. But before, let's see how can we write a recursive function. In general, a recursive function is made of two parts. The first part contains one or more base cases, and the second part contains one or more recursive cases. But it's not always the case. We can have recursive functions where the base case is implicit. We'll see an example later. Now, let's see some real code of examples we've seen before, and we start with the easiest one, factorial. Before writing a recursive function, we have to identify the base case of the problem and the relation between the different function calls. Here for factorial, the base case is when n is equal to 1. It's the simplest input for our function, because it's just equal to 1, so when n is equal to 1, we just return 1, because 1 factorial is 1. And for the recursive case, we know that the relationship is that factorial of n is n times factorial of n minus 1, so we just return n times factorial of n minus 1. That's it. And you can see that the recursive function is usually kinda short and elegant, which is nice. Oh, and by the way, for all the recursive function we will write, we will consider that the input is valid. For example, here n must be strictly positive because we would never reach the base case otherwise. Anyway, let's move to the second example, which is the Fibonacci sequence. Here is a definition of the Fibonacci sequence. Now pause the video and try to write the recursive function. Time for the solution now, which is quite easy. Here we have two cases where we can directly return the result. It's when the input is 0, because Fibonacci of 0 is just 0, and when the input is 1, because the result is 1. But we can merge them into one base case, and we write if n is smaller than or equal to 1, we return n. Else, we have the recursive case. We know that Fibonacci of n is just the sum of the two previous terms, so we return fib of n minus 1 plus fib of n minus 2. That's it. Note that this recursive implementation of the Fibonacci sequence is slow. We'll see the reason behind it and a better one later in the course. Third example, merge sort. We said that to sort an array by using the merge sort algorithm, we have to split it into two parts, sort the left part, sort the right part, and join them by keeping the result sorted. Except if the array has at most one element because it's already sorted, so we return it directly. It's the base case. Note that the merge sorted R function takes two sorted arrays as parameters and returns them merged into a sorted array. It creates an empty array, then it keeps taking the smallest element. Now for the merge sort function, we said that the base case is when the array has at most one element, so if the length is smaller than or equal to 1, then the array is already sorted. We just return it. Else, we first have to split the array into two parts, and in order to do that, we calculate the middle index, which is the length divided by 2, then the left part is the subarray from index 0 to mid, and the right part is the subarray from mid to the end. Now we sort the left part by calling the same function because it's recursive, then we sort the right part, and we return them merged into a sorted array, which is the input array but sorted. Fourth example, Tower of Hanoi. We want to create a function that prints the necessary moves to do to win the Tower of Hanoi game with n disks. And if you remember, we said that we have 3 pegs, the source, the auxiliary, and the destination, and to win we have to take n-1 disks from source to auxiliary, then we take 1 disk from source to destination, then we take those n-1 disks from auxiliary to destination. Except if we have only 1 disk where we just directly take it from source to destination, it's the base case. In code, the function takes 4 parameters, n, which is the number of disks, the peg that represents the source, at the beginning it's a, the peg that represents the auxiliary, at the beginning it's b, and the peg that represents the destination, at the beginning it's c. Now the base case, if n is equal to 1, we just print that we take a disk from source to destination. That's all we have to do. Else, we have 3 things to do. We take n-1 disk from source to auxiliary, then we print that we take a disk from source to destination, and we take n-1 disk from auxiliary to destination by calling the same function but with different parameters. You have to understand how I changed parameters when calling the function again, because in the first call, we wanted to take n-1 disks from source to auxiliary, not to destination. So in the destination field, I've put auxiliary and vice versa. In the auxiliary field, I've put destination. And for the second call, we wanted to take n-1 disks from auxiliary to destination. So in the source field, I've put auxiliary because we take from there, and vice versa. In the auxiliary field, I've put source. Now we move to another example, binary search. Remember that in binary search, we always compare with the middle, then we decide if the search value can only be in the left part or in the right part, and we keep repeating until either we find the element or there are no more elements left. So we have two base cases here. But to avoid always creating a new array, binary search is implemented with left and right pointers. They represent the array's boundaries, so we will always work on the same array, but in the part between left and right only. And because at the beginning we start searching in the whole array, then left starts at the first index and right starts at the last index. Now we compare the search value with the element at the middle, and if the search value is smaller, then we know that it can only be in the left half. So right, which is the right boundary of the array where we're searching, becomes mid minus 1, because now we will search in the left part only, which is between left and min minus 1. So we call the function again, but with left and min minus 1 as parameters. Else if it's the opposite, the search value is greater, so left becomes mid plus 1, because now we will search in the part between mid plus 1 and right. This is why we call the function again, but with mid plus 1 and right as parameters. Those were the recursive cases, but what about the base cases? You have to know that we have two base cases. The first one is when we have no more elements, in other words when left exceeds right, and in that case we return minus 1. It means that we didn't find the search value. And the second base case is when we find the element at the index mid. Remember that we always compare with the middle. In that case, we return mid because we are searching for the index of the search value. We move to the code now, and the function takes four parameters: r, which is the original array, num, which is the search value, and left and right, which are the boundaries of the part where we're searching. Then we calculate mid-index, which is left plus right divided by 2, because we are searching in the part between left and right only, and to get the index that is at the middle of that part, we calculate left plus right divided by 2. Now we have two base cases and two recursive cases. The first base case is when left is greater than right, we return minus 1 as explained earlier. And the second one is when r of mid is equal to num, the search value, we just return mid. Now the recursive cases. The first one is when r of mid is smaller than num. It means that num can only be between indexes mid plus 1 and right, so we return the result returned by the function called again with mid plus 1 and right as boundaries. You'll understand more how this process works in the second part of this lecture. And the second recursive case is when r of mid is greater than num. We return the result returned by the function called with left and mid minus 1 as parameters, because now num can only be between left and mid minus 1. And this recursive process gets repeated until we reach one of the two base cases, so we stop when either we found num or we have no more elements. Note that we may also need the small function that just calls the recursive function the first time, and we said that left and right are initially the first and last index of r, so left and right values are initially 0 and length of r minus 1 respectively. Last example, the file system. We said that we have a file system and we want to get the total size, knowing that the size of directory is the sum of sizes of files and subdirectories inside it. If we oversimplify the definition of a file and a directory, we can say that a file is made of its name, which is a string, its content, which is an array of bits, and its size, which is an integer that represents its size in bytes. And a directory is made of an array that contains files inside it and another one that contains subdirectories inside it. Now we can start. We want to get the size of our file system, which is the size of the root directory. And we said that the size of a directory is the sum of files and subdirectories inside it. And this is what we're gonna write in this function. We create a variable size initialized to 0, then for each file in our directory's files we add the size, which is one of its properties. Then we also need to get the sizes of the subdirectories, so for each subdirectory we get its size by calling the same function, because subdirectories are also considered as directories, and we add the size to our variable. After the loop, we can return our size variable that contains the size of the actual directory passed as a parameter. Now you may tell me that this function doesn't have a base case, but in reality it has one. It's just that it's not as explicit as previous examples where we used if-else statements. Here the base case is when the directory has no subdirectories. It means that this for loop won't be executed because dir.subdirectories will be empty, so the recursive function won't be called again. In brief, to write a recursive function you have to think about two things: base cases and recursive cases. Once you figure them out, the task becomes easy. And figuring out base cases and recursive cases is not always easy. It requires a lot of practice and a good understanding of the recursion's process. Speaking of the process, let's move to the second part where we'll see what happens when a recursive function is called. Okay, let's imagine that you want to calculate 5 factorial, but in order to do so, you need to have the value of 4 factorial, so you ask someone to calculate 4 factorial. But he needs the value of 3 factorial, so he asks another person to calculate it. Now you guessed it, he needs the value of factorial too, so he asks another person to calculate it for him. Again here, the one that will calculate 2 factorial needs the value of 1 factorial, so he asks another person for it. But now, this person knows the value of 1 factorial, which is 1, and he doesn't need another person, so he directly gives the value to the one that's gonna calculate 2 factorial. Let's name it fact2. Now fact2 has the value of 1 factorial, he just has to multiply it by 2 and he gets 2 factorial, and he returns the value to fact3. Now fact3 has the value of 2 factorial, he just multiplies it by 3 and he gets 3 factorial, which is 6, and he gives it to fact4. You guessed it, fact4 can calculate the value asked him for. By multiplying 3 factorial by 4, it gives 24. Now back to you can finally calculate 5 factorial, you just multiply 4 factorial by 5 and you get 100. In reality, each person is a function call in the story. You are fact5, you called fact4, fact4 called fact3, fact3 called fact2, fact2 called fact1, and because fact1 is the base case, then it didn't call the fact function again. So it returned 1, then fact2 returned 2 times the value returned by fact1, then fact3 returned 3 times the value returned by fact2, then fact4 returned 4 times the value returned by fact3, and then fact5 returned 5 times the value returned by fact4. If we made a function to each value, this is what we would write, but it's just to represent the situation. To better understand the recursion process, you have to know something important about function. It's that if a function has a function call inside it, not necessarily to the same function, then the code before that call will be executed, then the function call gets executed, then the code after that call gets executed. Little example, we have 2 functions. The first one prints that it's the first function, then calls the second function, then prints again that it's the first function. And the second function just prints that it's the second function. Now try to guess what happens when we call the first function. What happens is that func1 prints that it's the first function, then it calls func2, so func1 stops and waits for the end of the execution of func2. Now func2 prints that it's the second function, and it's the only thing it does, so its execution ends and we go back to func1 to continue the remaining instructions after the function call. Now it prints that it's the first function and the function ends. And calling a recursive function follows the same logic. The recursive function keeps calling itself until it arrives to the base case, then it goes back to the previous calls to continue remaining instructions until it arrives to the initial call. And you'll see it with this recursive function. This recursive function takes an integer n, prints it, then calls itself with n-1, then prints n again. And the base case is when n is 1, it just prints 1. Now pause the video and try to guess the output with n equal to 4. With n equal to 4, func4 prints 4, then calls func3, and it will wait for it to end so that it can continue its work. Func3 prints 3, then calls func2, func2 prints 2, then calls func1, and func1 is the base case so it just prints 1 and it ends. Back to func2, now it prints 2 and it ends. Back to func3, it just prints 3 and it ends. And back to func4, it prints 4 and it ends. And we can easily visualize the recursion in the output. The output represents func4, we have 4, then what got printed in func3, then 4. And for func3, we have 3, then what got printed in func2, then 3 again. And for func2, we have 2, then what got printed in func1, then 2. And func1 is the base case, we only have 1 printed. Another example now, we have this recursive function that looks like the previous one, but this one calls itself with n-1, then prints n that calls itself again with n-1. Here again, pause the video and try to guess the output with n equal to 4. With n equal to 4, func4 calls func3, and again here, func3 calls func2. Again, func2 calls func1. Now we reach the base case, so func1 just prints 1 and it ends. Back to func2, we continue instructions after that function call, so it prints 2 and it calls func1 again, which prints 1 and ends. Now func2 has no more instructions, so it ends, and we go back to func3. It prints 3 and it calls func2 again. Func2 calls func1, which prints 1, then ends. Then func2 prints 2 and calls func1 again. It prints 1 and ends. And func2 also ends because it doesn't have instructions left. Func3 also ends because of the same reason. Now back to func4, it prints 4, then calls func3 again. And the same process gets repeated and it prints 1, 2, 1, 3, 1, 2, 1. Here is a representation of what happened in the process. Now let's move to an important concept in recursion, the call stack. While explaining the execution of the previous examples, you probably wondered where are the function calls stored during the execution, because when a function call ends, it goes back to the one that called it, so the intermediate calls must be stored somewhere. And you have to know that they are stored in the call stack. First of all, what is a stack? A stack is a data structure that follows the LIFO principle, last in first out. It means that the last element that enters the structure is the first one that is gonna be removed. The opposite is also true, the first element that enters the structure is the last one that is gonna be removed. The opposite is also true, the first element that enters the structure is the last one that is gonna be removed. And the stack has 5 main operations. We have push to add an element on top of the stack, we have pop to remove the element on top of the stack, we have peek to get the value of the element on top of the stack, we also have isEmpty to check if the stack is empty, and we use it before popping an element, because if we try to pop an element from an empty stack, we get a stack underflow error. And we have isFull to check if the stack is full, and we use it when the stack has a fixed capacity and we want to push an element, because if we try to add an element to a full stack, we get a stack overflow. Yes, like the website. A real life example of a stack is when you discuss with a friend. For example, you start your discussion by talking about coding problems, and while talking about it, one of you brings a new subject, algorithms for example. So now you stop talking about coding interviews until you finish talking about algorithms. You added algorithms to your subject stack. Then while talking about algorithms, one of you starts talking about recursion, so you add recursion to your subject stack. Now you finish talking about recursion, so you go back to the previous subject, algorithms, to continue talking about it. After finishing it, you go back to coding problems, and when you finish talking about coding problems, then you don't have subjects left on your subject stack. Note that the process doesn't have to be push 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 pop 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 like we did here, this one was just an example. Now that you understood what is a stack, I can explain the call stack by answering 3 questions. What is the call stack, why do we need it in recursion, and what if a stack overflow happens? So what is the call stack? The call stack is a stack that holds information about the different active functions, return address, local variables, parameters, etc. And when we call a new function, that call is pushed into the call stack. Then when it ends, that frame gets popped from it and we go back to the previous call. Note that the call stack is implicit and automatically handled by the system, so you don't have to add additional instructions for it. Second question, why do we need the call stack in recursion? We need the call stack because, as you may know, in a recursive process, we usually have multiple active function calls, so we need a structure to know their order and their information. It's also useful to understand what happened during the execution. For example, to calculate 5 factorial, we first called fact5, here it is on the call stack, then before fact5 ends, it called fact4, so we add a new frame on the call stack. Same thing here, fact4 called fact3, we push. Fact3 called fact2, new frame on the call stack. And then fact2 called fact1, we add it. Now fact1 is the base case, it just returns 1 and it ends, so we pop its frame from the call stack and you can see that now we could know that we have to go back to fact2. Fact2 returns 2 and it ends, we pop. Fact3 returns 6 and it ends, so we also pop. Then fact4 returns 24 and it ends, we also pop it. And fact5 returns 120 and it ends, so we pop it, and we finish the recursive process by getting 120, the value returned by fact5. Now let's see another example where we have 2 function calls, merge sort for example, and we will apply it to sort this array of 8 elements. The first function call is the one that returns the whole array sorted, here it is on the call stack. It splits the array into 2 parts, and it calls the same function to sort the left part. This call does the same thing, it splits into 2 parts, then calls the function to sort the left part. Same thing again, we split and we sort the left part. Now we reach the base case, so the function call just returns R and we remove its frame from the call stack. Back to this call, we now have to sort the right part. And it's the base case, it directly returns R. Now we have both parts sorted, so we return them merged into a sorted array. Back to this call, we now have to solve the right part, so we split it into two parts. We call on the left part, but is the base case, we call on the right parts, also the base case, and we return them merged into a sorted array. Now we have both parts sorted, we return them merged. Back to the initial function call, we sorted the left part, and now we have to solve the right part. We split it into two parts, we solve the left part, and you know the process. We split it, left part, base case, right part, base case, and we return them merged. Now right part, we split, left part, base case, right part, base case, and we return them merged. Back to this call, we have both parts sorted, we return them merged. And back to the initial function call, we finally sorted both parts so we can return them merged into a sorted array, which is in reality the initial array but sorted. And from this example, you can deduce that we can push and pop from the call stack multiple times. It just depends on what the function does and how many times it calls itself. Okay, now let's move to the third question. What if a stack overflow happens? You have to know that the call stack has a fixed size capacity, so if it's already full and you try to add a function call on top of it, the program will probably crash. For example, in Python, the default maximum call stack size is 1000, so if you call fact of 1005 for example, you get this error, maximum recursion depth exceeded. But note that there is a technique called tail recursion optimization that can optimize a recursive function. By using it, holding the intermediate function calls will be unnecessary. We'll talk more about it later. Little recap of this lecture now, it covered three aspects: writing a recursive function, the recursive process, and the call stack. For writing a recursive function, we said that a recursive function is usually made of two parts, the base cases part and the recursive cases part, and that once you figure out base cases and recursive cases, the remaining stuff becomes quite easy. For the recursive process, we said that when a function calls another function, its execution stops until that new call ends and is the main concept used in a recursive process. A function keeps calling itself until it reaches the base case, then it goes back to the previous function calls to continue the remaining instructions. And for the call stack, we said that it's a stack used to handle the different active function calls, and it's very useful in recursion to keep track of the different recursive calls and their information. But be careful of the stack overflow. This lecture was quite long and maybe boring, but it's necessary to understand how recursion works under the hood, so ask questions if you didn't understand something, and see you in the next lecture. Welcome to this new video where we will talk about base cases and recursive cases. In the previous videos, we said that in a recursive function we have at least one recursive case, the case where the function calls itself again, and at least one base case, the case where the function doesn't call itself again, which is necessary to stop the recursive process and avoid the infinite recursion. If we don't have any recursive case, the function would never call itself again, so the function is not considered as recursive, and if we don't have any base case, the recursion would never stop, so we deduce that both of them are important. We have two types of base cases. We have the base case that occurs when there is nothing to do anymore, and the base case that occurs earlier because of a specific condition or something. Let me give you an example. We want to check if an integer n that is greater than 2 is prime. So we check if it has another divisor except 1 in itself. For that, we want to traverse all integers between 2 and n, so we put a parameter I that starts at 2. And now we have two base cases. We have the case where I reaches n, where we have no more possibilities. It means that we traversed all integers between 2 and n, and we didn't find any number that divides n, so n is a prime number. We return true. But we also have the case where the process finishes earlier, where while traversing integers, we find one that divides n. It means that n is not a prime number, so we directly return false. The iterative version of this function follows the same logic. We have the early return statement that gets executed when we find an integer I that divides n while looping, and we have the late return statement that gets executed after looping over all integers between 2 and n without finding one that divides n. Which means that when searching for base cases, you can start by searching for the late base case, the one that occurs where we have nothing to do anymore, or when the problem input is simple enough to be solved directly without calling the function again. But you also need to think about the early base cases, where we find the output of the recursive process earlier, or for example in backtracking, a technique based on recursion that you will see later in this course, when we find a situation that makes the actual potential solution invalid. In that case, we need a base case to directly backtrack without continuing the actual possibility, because we already know that it's not valid. Okay, now let's move to recursive cases. Same as base cases, we can have multiple recursive cases. For example, in binary search, when we still have elements and we didn't find the search value in mid-index, we have to continue searching. But we have the case where we search in the left part and the case where we search in the right part. So we need a recursive case for each one of them. We have the recursive case where num is greater than r of mid, where we call the function again to search in the right part. And we have the recursive case where num is smaller, where we search in the left part. And to search for recursive cases, you have to divide your problem into one or more smaller instances of the same problem. For example, in merge sort, we said that we can sort an array by dividing it into two parts and sorting them. So in the recursive case, it's what we do. We call the function again to sort the left part, then the right part. Then we combine the results by merging them into a sorted array. So, finding the recursive cases is all about dividing the problem into sub-problems of the same type, which means that when making a recursive function, before thinking about the code, you have to take some time to analyze your problem and think about two things: the way to divide it into sub-problems of the same type, to find the recursive cases, and the conditions where recursion has to stop, to find the base cases. And obviously, if you have multiple conditions, you can add more base cases and or more recursive cases to cover all the possibilities. I hope that you now know a little bit more about base cases and recursive cases, the two fundamental components of a recursive function. See you in the next lecture. Welcome to this new lecture where we'll see recursive functions with two or more recursive calls. A recursive call is when we call the same function again, so in our function, we can have calls for other functions, but when we call the same function, we say that it's a recursive call. And the majority of examples we've seen so far had only one recursive call, like with the factorial function. And the process of a recursive function with only one recursive call is pretty easy. We just keep calling the same function while pushing onto the stack, then once we reach the base case, results start going back until we go back to the initial function call. But what if we have more than one recursive call? An example of a function that has more than one recursive call that we've seen earlier is merge sort. In merge sort, we need two recursive calls, one to sort the left part and one to sort the right part. Before jumping to the process of how does it work, I want to clarify something important. I want to let you know that there is a difference between a recursive function with multiple recursive calls and one with multiple recursive cases. A function can have multiple recursive cases, like in binary search, an example that we've seen earlier. You can see that the recursive function has two recursive cases, one when the element at the middle is smaller than the element we're searching for, and one when it's greater. But in both of them, we perform only one recursive call, because as you may know, only one recursive case will be executed. They can't happen at once, so we will either call binary search function with mid +1 and right, or with left and mid -1. This is why in this recursive function, only one recursive call will be performed, and it will follow the process of going deep until reaching the base case, then going back. Which is the opposite of merge sort, where we have only one recursive case, but in which we will perform two recursive calls. And obviously, we can have a function that has multiple recursive cases and multiple recursive calls, like this one. In Brief, we have four types of recursive functions: one recursive case and one recursive call, like factorial, multiple recursive cases and one recursive call, like binary search, one recursive case and multiple recursive calls, like merge sort, and multiple recursive cases and multiple recursive calls, like the one we've seen now. When making this course, I asked the Inside Code Instagram community about their issues with recursion, and a frequent answer was recursion with multiple calls. And I think that this problem has two reasons: not understanding the process when there are multiple calls and not being able to visualize it. This is why now we will see the process, then in the next lecture we will see how to visualize it by using the recursion tree. First of all, what is a tree? A tree is a recursive data structure where every element is called a node. A node contains a value and references to its children, as you can see. The thing is that the top node of a tree is called the root, and it contains references to subtrees. But subtrees are also considered as trees, so we can say that the tree data structure is made of a root and subtrees, which are also trees. And the same thing gets repeated: subtrees of subtrees are also trees. The recursive nature of a tree also appears in its definition, because we can define the tree class as a value of any type and an array of elements of type tree. They represent the children. There is a particular type of tree that you'll often hear about is the binary tree. It's a tree where a node can have at most two children named the left child and the right child. This is why we don't need to use an array. Instead, we use two attributes left and right. Now let's see how to traverse the elements of a tree. Traversing a tree can seem quite confusing at the beginning because a tree is a non-linear data structure. An example of a linear data structure is the array. To traverse it, we can just start from the first element and walk straight forward. But the tree is non-linear, so it doesn't have a straight path. It has multiple branches and paths. But don't worry, I'll show you how we can traverse it. You have to know that we have two popular ways to traverse a tree. We have the depth first search traversal, DFS, and the breadth first search traversal, BFS, and they both start from the root. In this course, we only need DFS, so let's see how it works. Let's start with the binary tree. In the name depth first search, we have the word depth. The idea of this traversal is to go deep into a particular path, then once we have no more way to continue, we go back to the previous node and we go deep into another path and so on until we traverse the whole tree. In Brief, to traverse a binary tree using DFS, we print the root, we traverse the left subtree, and we traverse the right subtree. But we said that subtrees are also trees, so to traverse the left subtree, for example, we print the root, we traverse its left subtree, then its right subtree. This is why I told you that it's recursive. So if we want to print values of this binary tree, this is what happens. I know that I didn't give enough details about how that happened, is because I'll do it with the first example that we will see, how to get the sum of elements of a binary tree. The code of printing values of a tree is pretty simple, to be honest. It's a recursive function obviously, where the base case is when the node doesn't exist, we just return to exit. Else we print the data stored in it, we call the function again to traverse the left subtree and again to traverse the right subtree. And for an n-ary tree, a tree where a node is not limited to two children, we can't do the same thing, but instead of calling the function with left and right, we have to traverse the array of children. Now let's move to the first example, the sum of elements of a binary tree. To get the sum of elements of a binary tree, if the node doesn't exist, we just return 0. Else, we get the sum of elements of the left subtree, we get the sum of elements of the right subtree, and we return their sum plus the root's value. You can see that in this function, we have two recursive calls, so let's see what happens with this example. An important thing that you need to know before we start is that the two recursive calls don't happen simultaneously. While the first call is getting performed, the function stops and waits for it to end, then when it ends, it moves to the second one. You'll see it now anyway. Let's start. The root has the value 5 and now we need to get the sum of its left subtree, so we call the same function on it. Now the root of this subtree is 8, we first calculate the sum of its left subtree. Left subtree now, again, we call on the left subtree. And now the left child is null, so the function returns 0. Same thing for the right child, it returns 0. And 7 plus 0 plus 0 is 7, so the sum of elements of this subtree is 7. Back to this call, we go to the right now, but it's null, it returns 0. We have 7 from the left, 0 from the right, 3 as root's value, so the sum is 10. We got the sum of this subtree. Back to this call, we go to the right, and from here left subtree, null, 0, right subtree, null, 0, we add the root value and we get 4. Now we have 10 from the left, 4 from the right, and by adding 8 we get 22. Back to the initial function call, we calculate the sum of elements of the right subtree. We go to the left, we have 9, from the right, nothing, and plus 1 we get 10. 22 plus 10 plus 5 is 37, so our function returns 37. It's the sum of elements of the whole tree. You need to understand three things from this process. The first one is that function calls don't happen simultaneously. As you could see, the function waited to get the sum of the whole left subtree, then it moved to the right one. Second thing, when we reach the end of a function call, we go back to the one that called it. Third thing, here we are pushing and popping calls multiple times in the call stack. Remember that when we have a new call, we push it onto the stack, then when it ends, we pop it and we backtrack to the previous call. Okay, now let's move to an example where we have more than two recursive calls. I could do the same example with an n-ary tree, but we're gonna see a totally different example. We will solve the ways to climb stairs problem. The problem says that we have stairs with n steps and a set of possible jumps, and we have to determine the number of possible ways to reach the last step. For example, here we have 10 steps and we can jump by 2, 4, 5 or 8 steps. The output will be 11 because we have 11 possible ways. We have 22222, 2224, 2242, 2422, 4222, 244, 424, 442, 5528 and 82. Now pause the video and try to find a way to solve this problem by using recursion. Let's start. Let's analyze this example. We can jump by 2, 4, 5 or 8 steps. So to jump to the last step, step number 10, we must either be 2 steps far from it, or 4, or 5, or 8. This is why we can say that the number of possible ways to jump to step 10 is the number of possible ways to jump to step 10 minus 2, 8, plus ways to jump to step 10 minus 4, 6, plus ways to jump to step 10 minus 5, 5, plus ways to jump to step 10 minus 8, 2. And you can see that it's a recursive process. So for example, to jump to step 8, we have to get the sum of ways to jump to step 6, to jump to step 4, to step 3, and to step 0. And this process gets repeated until we reach the base case, which is wanting to jump to step 0, where we know that we have only one way to go to it, it's by not jumping at all, so we return 1. In code, our function takes n, the number of steps, and possible steps, the array that contains the possible amounts of steps that we can jump by. The base case is when n is 0, as said earlier, we return 1. Else, we create a variable nb ways to solve the sum, then for each steps in possible steps, if n minus steps is positive, we add the number of ways to jump to n minus steps. The condition of n minus steps being positive is important because we can't jump to step minus 1 or minus 2 for example. After the loop, we just return nb ways. It's possible that you didn't fully understand the process of this second example, but don't worry, you'll better understand in the next lecture because we'll visualize the process through the recursion tree. See you there. Welcome to this new lecture where we'll talk about the recursion tree. In the last lecture, we've seen the recursive process of a function that has 2 or more recursive calls, which can be sometimes hard to visualize. This is why we have to learn about the recursion tree. What is the recursion tree? The recursion tree is a tree where every node represents one subproblem and the relation parent-child means that the parent called the child. I use the term subproblem because recursion is all about dividing the problem into smaller subproblems of the same type, solving them, then joining the results. For example, in merge sort, we split the array into 2 parts, then we sort them, so we kinda divide the problem into smaller subproblems of the same type, sorting smaller parts of the array. Now the question is, how to draw a recursion tree? To draw a recursion tree, we first draw the root, which is the initial function call, then every time we perform a new recursive call, we draw a child. An example is better to understand, so let's take our treesome example, and let's draw the recursion tree. The initial function call is performed on the root, the node that contains the value 5. So in our recursion tree, the root contains the function name and the parameters of that call, the node with value 5 here. You don't necessarily need to write the function name by the way, you can just put the parameters, it's as you want. Now we want to get the sum of the left subtree, so we call the function again on the node whose value is 8. This is why we draw a new child in our recursion tree that represents this function call. We continue, we also want the sum of the left subtree here, we draw a new node. Left subtree again, we draw a new node. Same thing again, we draw a new node. Here we reach the base case represented by a leaf in our recursion tree. In definition, a leaf is a node that has no children, which is the case here. The base case doesn't perform any recursive call, so it has no children, and in our case, it returns 0. We backtrack and we go to the right. Same thing, base case, we backtrack. Here we got the sum of both subtrees, so we backtrack, then we go from the right. I think that you started understanding the process because the recursion tree is having the same structure as our input tree. So here is our recursion tree at the end of the process. It contains all the function calls we performed, and we can easily get their order by traversing it in depth first search. This example is quite easy to visualize because we already have the input tree, so if you know that first search traversal, you can directly know the order of the function calls. But it's not always that easy, like with the example that we will see now, ways to climb stairs. I explained the solution in the last lecture. We said that to get the number of ways to the step n, we calculate the sum of ways to jump to each step from where we can reach the step n. Let's take the example we've seen and see the process while building the recursion tree. But before, please pause the video and try to draw the recursion tree. It's very important to practice. Okay, let's start. We want to get the number of ways to reach step 10, so the initial function call is ways of 10. I know that the function takes 2 parameters, but possible states array doesn't change, so we can decide to put values of parameters that change during the process only, the value n in our example. Now we need to get the sum of ways to go to step 8, 6, 5, and 2. We start with step 8. Here is the function call. Same thing again, we need ways to go to 2 steps away from step 8, and 8 minus 2 is 6. We didn't reach the base case yet, so we continue. We count ways to go to step 4. We repeat step 2. We repeat step 0. And here n is equal to 0 is the base case, so we return 1, as explained in the last lecture. Now 4 steps away is 2 minus 4, which is negative, we don't call. Remember the condition. Same thing for 5 and for 8. The sum of values returned from children is 1, so we return 1. It means that we have 1 way to go to step 2. Now 4 steps away gives 0, the base case, we return 1. And we can neither subtract 5 nor 8, because the result is negative. We cannot jump to a negative step. We have 1 plus 1, which is 2, so we return 2. Now 4 steps away from 6. Now 2 steps away from 2, we get 0, the base case, so we return 1. Again here we have only one child, the sum is 1. Now 5 steps away, we can't perform any recursive call because all possible jumps are above 1, so the sum is 0. Be careful, here is not the base case of n being equal to 0. We have no calls just because all possibilities are above 1. This is why our sum variable receives no value to add, it remains 0. In other words, we have no way to go to step 1 and you can verify it by yourself. Back to this call, we can't go 8 steps away because it would be negative, so we have 2 plus 1 plus 0, which is 3. In other words, we have 3 ways to go to step 6. And let me just let the animation continue the work. As you can see now, we finished making the recursion tree and we got that the number of ways to go to step 10 is 11. Please take some seconds to analyze this recursion tree. And what's amazing with this recursion tree is that every path from the 0 base case to a node represents one way to go to that step. For example, this path represents one possible way to go to step 8. We pass from steps 0, 4, 6, 8. And this one represents one possible way to go to step 10. We pass from steps 0, 2, 4, 6, 10. Second thing, every value returned by a node represents the number of ways to go to that step. For example, ways of 6 return 3, so we have 3 ways to go to step 6. This is true, we have 0, 2, 4, 6, 0, 4, 6, and 0, 2, 6. Ways 3 return 0, so we have no way to go to step 3, which is also true. Before ending this lecture, let me clarify 3 things. First of all, unlike the call stack, the recursion tree is not saved in the memory, it's just a way for us to visualize what happened during the recursive process. Second thing, you have to know that executing a recursive function doesn't show you the recursion tree, you have to add some instructions for that, and this is what we will see in the next chapter. And third thing, from this recursion tree, you can notice that sometimes we are repeating work that we already did, same color means the same call. For example, here we calculated the number of ways to go to step 6, we found 3, then we needed that value again here. You can see that we did all the work again. In Brief, we have repeating function calls that are consuming time uselessly. And the idea to fix this problem is to store results that we computed before. For example, when we find out that we have 3 ways to go to step 6, we store it somewhere so that the next time we need to know the number of possible ways to go to step 6, we directly take it from where we stored before instead of doing all the work again. We can do so by using memoization or dynamic programming. We will see both of them in a further chapter. Bonus info, in this function we had a hidden base case, it's when all possible jumps are above n, like with the value 1 in our example. You can see that we didn't perform any recursive call, it's a leaf so it's a base case. Little recap, the recursion tree is a tree that keeps track of the recursive calls we're performing during the process. It contains the function calls, which call called which call, and the value returned by each call. The root represents the initial function call and leaves represent base cases. It helps us to visualize how we've been able to get the value returned by the initial function call recursively. And to draw it, we just draw the root, and every time we have a new recursive call, we draw a children node and we go to it. Then when a call returns a value, we write it in the link between that call and the call that called it, and we backtrack. And to read the recursion tree, we just perform a depth first search traversal on it to know the order of function calls. I hope that now you know how to draw and read the recursion tree. Ask me questions if you didn't understand something, and see you in the next lecture. Welcome to this new video where we will see how to visualize the call stack. Little recap, we said that the call stack is a stack stored in memory. It contains information about the different active function calls, and each stack frame contains the local variables, the parameters of that call, the return address, etc. And every time there is a new recursive call, a new stack frame is pushed into the call stack, and then when that call ends, it gets popped from the call stack. And the call stack is really helpful to visualize the recursive process, but the problem is that it doesn't get printed when performing a recursive call. I mean, the call stack is actually in memory and we aren't visualizing it during the recursive process, so the idea is to kinda create a stack that stores the different active function calls so that we can print it and see what's actually happening. We said that we push when we have a new recursive call and we pop when it ends. Now the question is, how can we implement that in code? First of all, you have to know that we can't just use an array without creating a stack class or something. Second thing, to push and pop the different recursive calls, we add a parameter to our recursive function named callStack, for example. Oh, by the way, the orange boxes don't matter, it can be anything, it's just to show you the usual structure of a recursive function. Then the idea is that when we enter the function, we push onto our stack the function name plus the parameters and we print to see the new state of the call stack. And before ending the function, just before the return statements, we pop the actual call and we print again. Let's do that with our merge sort function. We add a parameter named callStack, then before any statement, we append merge sort plus the array we're sorting, and we print. And before every return statement, we pop and we print again. Now let's try it with this array. We create the callStack and we call our merge sort function. You can see that it printed the different states of the call stack during the recursive process. The first call wanted to sort the whole array, so it first called merge sort to sort the left half, and the left half also called merge sort to sort its left half, then left half again, here we reached the base case, so it went back to the previous, then right half, also base case, it went back, and so on until the whole array got sorted. You know the process. And you can see that by keeping track of the different calls, we can step by step analyze which call called which call, and it helps to understand the recursive process. Here is a little animation for you to visualize what happened. Little recap, to visualize the different recursive calls of the recursive process, we can use a stack, and in our recursive function, we add a parameter callStack, we append a string that contains the function name plus the parameters and we print, and before every return statement, we pop and we print again. And before calling our recursive function in the main, we create an array that will act as a stack. I hope that you now know how to visualize the recursive process with the call stack, try to implement it with another function that we made, and see you in the next video. Welcome to this new video where we will learn how to visualize the recursive process by using a recursion tree. We already introduced the recursion tree in the previous videos. We said that it's a tree that contains the different recursive calls executed during the recursive process, the links that show which call called which call, and the value returned by each recursive call. We also said that the roots represent the initial function call and the leaves of the tree represent base cases. And I told you that the recursion tree is a very good way to visualize the process, because it gives you a global schema of what happened during the execution, so by performing a depth first search on it, you can get the chronological order of the different recursive calls. But same as for the call stack, when calling a recursive function, the recursion tree doesn't get printed, so we will have to implement it by ourselves. For that, you have two choices. You can either draw it yourself by hand, which is kinda slow and maybe error prone, or you can do what we did with the call stack, implementing it in code. You create a tree and keep updating it every time there is a new recursive call, and this is what we will do now. But it will be a little bit more difficult here, because we first need to create the tree class, then find a way to save the different function calls, and then find a way to print the tree we made. Okay, let's start with the tree class. We want to save the different function calls, so one node from the tree will contain the call, which is a string that contains the function name plus the values of the parameters, the value that it returned, and an array that contains the recursive calls it performed. In code, the constructor of our class initializes the call to an empty string, we'll update it later, same thing for the returned value, now we just put null, and for the children, we initialize it to an empty array. Now the second step, we will add some code to keep track of the function calls and add them to our tree. The idea is to add a parameter to our recursive function, which is the node that represents the actual recursive call. And inside the function, before any statement, we update the string that represents our call, we put the function name, then between parentheses, we put changing parameters only. For example here, I didn't put possible steps array because it won't change during the process, we don't need to see it every time, we just need to see the value of n that represents the number of remaining steps. Then before any recursive call, we create a new child, we put it in children of the actual node, and when calling the function again, we pass the child as a parameter, because it represents the node of the recursive call called by the actual node. And before every return statement, we first save the returned value in the returned attribute, then we return. We did that because we need to save the value returned by each call. And in the main function, we first create the recursion tree, it's actually empty, we pass it as a parameter when calling our recursive function, and then we print it to visualize it. But we didn't talk about the print tree function yet, let's do it. First of all, why is printing a tree different from printing an array, for example? It's different because the tree is a non-linear data structure, because unlike the array, it doesn't have a clear straight path of how to print it. Printing an array is easy because we just start from the first element and we keep printing. Yes, we can kinda do the same thing with the tree, we just traverse it in depth first search and keep printing. But the problem is that we can't visualize the hierarchy, we can't see which called which. So we want to print the tree by keeping the hierarchy like this. This function recursively prints our tree by printing the call and return value of the actual node, then for each child, it prints the indentation, it prints 4 dashes, and it calls the function again to print that subtree. Note that the indentation keeps growing at each level of the hierarchy as you can see. This is why at the end, it gives us a nicely displayed tree that you can easily compare with the original one. And this principle is also used in the command line to print the directory tree structure. For example, if you're on Windows, go to CMD and write tree and press enter. In brief, in this lecture, we learned how to create a tree to visualize the recursion tree of our process, because visualization is very important to understand recursion. We said that we need to create the tree class, then add some code in our recursive function to store the different calls and their hierarchy, and then use the print tree recursive function that you can find below to print the recursion tree we made. I hope that you now know how to draw a recursion tree, how to read it, how to traverse it to get the chronological order, and how to add code to print it after the process. If you have questions, don't hesitate to ask me below, check the code, and see you in the next video. Welcome to this new video where we'll talk about complexity analysis of recursive functions. When analyzing the time complexity of a non-recursive algorithm, we just do the sum of operations of each instruction, then deduce the time complexity. We can do so because we have the number of operations of all the instructions. Let me explain. Let's take a non-recursive algorithm, this one for example. We find out that this instruction costs n, this one costs n squared, and this one costs 1. We do the sum, we take the greatest term, and we get a time complexity of O of n squared. But if we take a recursive algorithm, merge sort for example, we know that splitting an array into 2 parts costs n by 2 plus n by 2, which is n. Joining them costs n, but sorting them recursively costs t of n by 2 plus t of n by 2, because we're using the same function to sort an array of n by 2 elements. And the problem is that we don't have the value of t of n by 2, so we cannot directly deduce the complexity. An idea that may come in your mind is to calculate t of n by 2, then move to t of n. So now you want the cost of sorting an array of n by 2 elements. splitting an array of n by 2 elements into two parts costs n by 2. Joining those two parts costs n by 2. But recursively sorting those two parts costs t of n by 2 by 2 plus t of n by 2 by 2, which is 2 times t of n by 4. You can see that we're facing the same problem again. We don't have the value of t of n by 4. Does it mean that it's impossible to analyze the complexity of a recursive function? No. During this chapter, we will see 3 methods to do so: the recursion tree method, the reconciliation method, and the master theorem method. But before, you have to know something about recursive functions. A recursive function solves a problem by splitting it into smaller instances of the same problem, solving them, then combining the results. So, a recursive function has 3 costs: splitting the problem, solving the subproblems, and combining the results. In the case of merge sort, splitting the problem represents splitting the array into 2 parts, solving the subproblems represents recursively sorting the 2 parts, and combining the results represents joining the sorted subarrays into a sorted array that represents the initial array but sorted. We can know the cost of splitting the problem. In merge sort, it's n. We can also know the cost of combining the results. In merge sort, it's n. But solving the subproblems is done recursively, so we face the problem of not knowing the cost. And the idea to calculate the time complexity of a recursive function is to do the sum of all the instructions except calling the function again of all the recursive calls. It represents the total cost of the recursive process. Now let's move to the next videos where we will learn how to analyze the time and space complexity of a recursive function. Welcome to this new video where we will learn how to measure the time complexity of a recursive function by using the recursion tree. To measure time complexity by using a recursion tree, we first draw a recursion tree that is as big as possible, then do the sum of the cost of splitting and combining of all the recursive calls where it enters the recursive case, add to it the sum of costs of base cases, and deduce the time complexity. Let's do it with the binary search function. And here is a recursion tree for this input. Here, splitting into subproblems is just choosing the boundaries of the subpart where we will search in the next recursive call. The cost is constant. And we have no cost of combining the results. We have only one result because we have only one recursive call. The total is constant of 1. Same thing for the base case, we're just returning a value. Which means that now we just need to calculate the number of recursive calls and multiply by 1. At the beginning, we still have n elements to check, and the base case is when we have no more remaining elements. So we need to count the number of required calls to go from n to 0. The idea of binary search is that we keep dividing the number of remaining elements by 2 until we reach 0. So the number of calls that enter the recursive case is just the number of required divisions by 2 to go from n to 0. And that number is tail of log 2 of n plus 1. So in the worst case, we have log 2 of n plus 1 function calls that enter the recursive case, and each call has a constant required cost to split and recombine. We got log 2 of n plus 1. We add to it one call that enters the base case, it has an O of 1 cost, we add 1. From this expression, we find out that the time complexity of binary search function is logarithmic of log n. Let's do a second example, the merge sort function. Let's analyze what is our function doing. In the recursive case, except performing recursive calls, our function is creating the left part of R n by 2 operations, creating the right part of R n by 2 operations, and returning both parts joined, which requires n operations. The total is 2n, but we can just simplify it to n by removing the constant. So when passing an array of n elements to one merge sort call, the cost of splitting and recombining is O of n. Now let's move to the recursion tree. The initial function call is performing n operations and performing 2 recursive calls. But here, the array passed as a parameter has only n by 2 elements because it represents only one part from R, either the left part or the right part. So the cost of splitting and combining in each function call is n by 2 operations. But each one of them calls the function twice with the array divided by 2 again, and divided by 2 gives n divided by 4, so the cost of splitting and combining in each function call is n by 4 operations, and so on. At the first level, we have one call that costs n. At the second level, we have 2 calls that cost n by 2 operations, and 2 times n by 2 is n. At the third level, we have 4 calls that cost n by 4, and 4 times n by 4 is n. So you can see that at each level we have n operations, and now we just need to know the number of levels of our recursion tree where we enter the recursive case, then multiply by n. At the beginning, R has n elements, and the base case is when R has only one element or less. And at each level, we are dividing the size of R by 2, so we just need the number of required divisions by 2 to go from n to 1. That number is log 2 of n, so we multiply n by log 2 of n, we get n log 2 of n. And at the bottom of the tree, we have n calls where it enters the base case, and each one of them costs O of 1, because we just return R, so we add n times 1. This expression gives a time complexity of O of n log n. We can say that the merge sort function runs on linear arithmetic time complexity, O of n log n. Another example, let's go. Let's get the time complexity of ways to climb stairs recursive solution. To solve this problem recursively, to get the number of ways to climb to the nth step, we get the sum of ways to climb to each step from where we can likely jump to the nth step. In the ways to climb function, we are traversing all the possible steps, so if we represent the number of possible steps by m, we can say that when it enters the recursive case, this function costs m operations plus the cost of recursive calls. I know that we have other operations like nb ways creation and returning, but we can't ignore them because they are single operations. Let's move to the recursion tree. At the first level, we have one call of m operations, and it's calling the function again m times in the worst case. Each one of them is performing m operations and is calling the function again m times in the worst case. I know that is not the case here, but in complexity analysis, we usually search for the upper bound, which is what we're doing here. Now each one of these m squared function calls is performing m operations and calling the function again m times in the worst case, and so on. So we have one call of m operations, m. Then at the second level we have m calls of m operations, m squared. Then at the third level we have m squared calls of m operations, m cubed, and so on until m power k. Now we need to find k, the number of levels where it enters the recursive case. In the worst case, we go back by one step only, so at each level n decreases by 1 only, so k is n. Our sum is m plus m squared plus m cubed, and so on until m power n. And we have m power n calls where it enters the base case, each one of them costs O of 1, so we add m power n. We have the sum of m power k where k goes from 1 to n, it's equal to m divided by m minus 1 times m power n minus 1. M divided by m minus 1 is close to 1 for large values of m, so we can just put 1. We got m power n minus 1. T of n is equal to m power n plus m power n minus 1, which is 2 times m power n minus 1. We take the greatest term, we remove the constant, and we get a time complexity of O of m power n. We can say that the ways to climb recursive solution is in O of m power n. But you have to know that m power n is not the tight upper bound, because in the worst case we have n steps and possible jumps are 1, 2, 3, 4, and so on until n. The next level of the recursion tree will contain ways to climb n minus 1, ways to climb n minus 2, and so on until ways to climb 0. That means that the more we go to the right, the more the branch will be shorter. The recursion tree will look like this at the end. So all that part is missing, m power n is not the tight upper bound. A last example, here we go. Let's measure the time complexity of the Tower of Hanoi function. In the recursive case, except calling the function again, we are just printing the move, so it's constant, same thing for the base case. Now we need to count the number of recursive calls. Here is the recursion tree with n equal to 4. At the beginning, we have only one call, the initial function call. Then it calls the function twice, and each call calls the function twice, and so on. So the number of function calls is getting doubled at each level. And for the number of levels, at each level, n is decreasing by 1, so we will have n levels. The total number of function calls is 2 power 0 plus 2 power 1 plus 2 power 2, and so on until 2 power n. This sum gives 2 power n plus 1 minus 1. Which is 2 times 2 power n minus 1. We remove smaller terms, we remove the constant, and we get a time complexity of O of 2 power n. In brief, to measure the complexity with the recursion tree method, you can follow these steps. Identify the cost of splitting the problem and combining the results in the recursive case, identify the cost of the base case, draw the recursion tree, count the total cost of splitting and combining in calls where it enters the recursive case, add to it the total cost of calls where it enters the base case, and simplify the expression to get the time complexity. But this method isn't the most recommended one. In the next video, we will see the recurrence relation method, a mathematical method that we will use to identify the time complexity of a recursive function. See you there. Welcome to this new video where we will learn how to identify the time complexity of a recursive function by using the recurrence relation method. The idea is that we keep replacing the cost of recursively solving the subproblems until we reach the base case. At that time, we'll have the total cost of the recursive process. Okay, let's take the factorial function for example. You can see that in the recursive case, we are calling the recursive function again with n-1, then performing the multiplication and returning. So if we want to count the number of operations of fact of n, we first need to calculate the number of operations of fact of n-1. If we represent the number of operations of fact of n by t of n, we can say that t of n is equal to t of n-1 plus 2. 2 is a constant, so we can just write 1 instead. Now we have this expression, but we can't calculate it because we need t of n-1. So what we're gonna do is that we will replace t of n-1 by using the expression we made now. We said that t of n is equal to t of n-1 plus 1, right? So we can say that t of n-1 is equal to t of n-1 minus 1 plus 1, which is t of n-2 plus 1. We replace in the expression. We now have that t of n is equal to t of n-2 plus 1 plus 1. We can remove parentheses. But same problem again, we don't have t of n-2, so we replace it. T of n-2 is equal to t of n-2 minus 1 plus 1. We replace in the expression and we remove parentheses. Same problem again, we don't have t of n-3. We replace it by t of n-4 plus 1 and we remove the parentheses. We still have the same problem. Does it mean that we're gonna do this infinitely? The answer is no, because now we need to find the general expression. Here we have t of n is equal to t of n-4 plus 4. And here the relation is easy. We know that if we continue, we will always have t of n being equal to t of n-k plus k, because we have t of n-1 plus 1, then t of n-2 plus 2, then t of n-3 plus 3, then t of n-4 plus 4, and so on. Now we need to know the cost of the base case of this function. The base case here is when n is equal to 1, and we directly return, so we have only one operation. We can say that t of 1 is 1. Okay, we go back to our expression. Now we need to find the value of k that will take us to the base case. Here we want to go to t of 1, because we know its value. n minus k equal to 1, so k is equal to n-1. We replace k by n-1 in our expression. We get t of n is equal to t of n minus n plus 1 plus n-1. n minus n plus 1 is equal to 1, so t of n is equal to t of 1 plus n-1. Remember that we know the value of t of 1, it's 1, so we can replace. T of n becomes equal to 1 plus n-1, which is n. Now we found the value of t of n with no cost of recursive calls on the right. We can say that the time complexity of our function is O of n. Basically what we did here is that we used the recurrence relation t of n equal to t of n-1 plus 1, and we kept replacing until we reached the base case, which is t of 1. You'll better understand with more examples. Let's do binary search function. Let's start by identifying the cost of the base case. Here in both base cases, we just return one operation, so we write t of 0 is equal to 1. 0 because the worst case occurs when there are no elements left, the size is 0. Now in the recursive case, we just return the recursive call, but as said earlier, in binary search we divide the number of remaining elements by 2, so we write t of n is equal to t of n by 2 plus 1. Here we didn't write 2 times t of n by 2 because even if the code contains 2 recursive calls, but only one of them gets performed, it's an if-else statement. Now we replace t of n by 2 by t of n by 2 by 2 plus 1, which is t of n by 4 plus 1. We replace again, we replace t of n by 4 by t of n by 8 plus 1, and we remove parentheses. Again, we replace t of n by 8 by t of n by 16 plus 1, and we remove parentheses. One more time, we replace t of n by 16 by t of n by 32 plus 1 and we remove parentheses. Okay, now we have t of n is equal to t of n divided by 32 plus 5, and we are at the 5th iteration. Now we need to find the general expression with k like we did earlier, and in our case, it's t of n divided by 2 power k plus k. We know that our base case is t of 0, so we need to find the value of k such that n divided by 2 power k becomes 0. In other words, we need to find the number of required divisions of n by 2 to reach 0. We need to divide n by 2 log 2 of n plus 1 times to reach 0, so we replace k by log 2 of n plus 1. T of 0 is 1, so T of n is equal to 1 plus log 2 of n plus 1, which is log 2 of n plus 2. We remove smaller terms and we get a time complexity of O of log n for binary search. Next example, Tower of Hanoi. In the base case, we are just printing only one operation, and it's when n is 1, so we write T of 1 is equal to 1. And in the recursive case, we call the function twice with n minus 1, and we print once, so we write T of n is equal to 2 times T of n minus 1 plus 1. We replace T of n minus 1 by 2 times T of n minus 2 plus 1, and we simplify. Now replace T of n minus 2 by 2 times T of n minus 3 plus 1, and we simplify. Again, we replace T of n minus 3 by 2 times T of n minus 4 plus 1, and we simplify. We get 2 power 4 times T of n minus 4 plus 15, and 15 is 2 power 4 minus 1. Now we can identify the general expression with k. It's 2 power k times T of n minus k plus 2 power k minus 1. The base case is T of 1, so we have to find the value of k such that n minus k is 1. It's n minus 1 because n minus 1 is 1. So we replace k by n minus 1 in the expression. We get 2 power n minus 1 times T of n minus 1 plus 2 power n minus 1 minus 1. N minus n plus 1 is 1 and T of 1 is 1. We get 2 power n minus 1 plus 2 power n minus 1 minus 1, which is 2 times 2 power n minus 1 minus 1, which is 2 power n minus 1. We remove smaller terms and we get a time complexity of O of 2 power n. Next example, merge sort. In merge sort, the base case is when the array has only one element or less and we directly return it, so we perform only one operation. This is why we write T of 1 is equal to 1. And in the recursive case, we have calculating mid-index, one operation, creating the left part, and by two operations, creating the right part, and by two operations, merging the sorted parts and operations, calling the function with the left part that has n by 2 elements, T of n by 2, and calling the function with the right part that has n by 2 elements, T of n by 2. So we write that T of n is equal to 2 times T of n by 2 plus 2n plus 1. But we can simplify 2n plus 1 to n. Now we replace T of n by 2 by 2 times T of n by 4 plus n by 2 and we simplify. We replace T of n by 4 by 2 times T of n by 8 plus n by 4 and we simplify. We replace T of n by 8 by 2 times T of n by 16 plus n by 8 and we simplify. We replace T of n by 16 by 2 times T of n by 32 plus n by 16 and we simplify. I think that we did enough iterations to deduce the general expression with k. Here it's 2 power k times T of n divided by 2 power k plus k times n. The base case is T of 1, so we search for the value of k so that n divided by 2 power k becomes equal to 1. The value of k here is log 2 of n, because 2 power log 2 of n is equal to n, and n divided by n is 1, so replace k by log 2 of n. 2 power log 2 of n is n, T of 1 is 1, we get that T of n is equal to n plus n log 2 of n. We remove smaller terms and we get a time complexity of O of n log n. Last example, ways to climb stairs. The base case is when n is 0 and we just return 1, so we have one operation. We write T of 0 is equal to 1. And in the recursive case, we are creating nb ways, one operation, traversing the n possible steps while comparing and calling T of n minus 1 in the worst case. And in turn in nb ways, one operation. The total is m times T of n minus 1 plus m plus 2, but we can simplify m plus 2 to m. We replace T of n minus 1 by m times T of n minus 2 plus m, and we simplify. We replace T of n minus 2 by m times T of n minus 3 plus m, and we simplify. We replace T of n minus 3 by m times T of n minus 4 plus m, and we simplify. Here we started noticing the pattern. We can find the general expression with k. It's m power k times T of n minus k plus m power k plus m power k minus 1, and so on until m squared plus m. The base case is T of 0, so we search for the value of k such that n minus k becomes 0. Here it's n, so we replace k by n, T of n minus n is T of 0, and T of 0 is 1. Here we have the sum of powers of m power k, where k goes from 1 to n. It's equal to m divided by m minus 1 times m power n minus 1. M divided by m minus 1 is close to 1 for large values of m, so we can just put 1. We got m power n minus 1. T of n is equal to m power n plus m power n minus 1, which is 2 times m power n minus 1. We take the greatest term, we remove the constant, and we get a time complexity of O of m power n. Now we've seen 5 examples on how to use the recurrence relation to identify the time complexity of a recursive function. The steps are: identify the number of operations of the base case, identify the recurrence relation from the recursive case, simplify the right part if possible, keep replacing until you start noticing a pattern, write the general expression with k, find the value of k to reach the base case, replace k by that value, simplify, and determine the time complexity. I hope that you understood the recurrence relation method. Don't hesitate to ask if you have questions, and see you in the next video. Welcome to this new video where we'll see the master theorem method, another method to identify the time complexity of a recursive function. The master method says that if our recurrence relation follows a particular generic form, we can directly identify the complexity without replacing and doing all that stuff. That generic form is t of n equal to a times t of n divided by b plus f of n, where a is a constant and positive, b is constant and strictly positive, and f of n is an asymptotically non-negative function. Here a represents the number of subproblems, b represents the value by how much we divide the input, and f of n represents the required time to create subproblems and combine the results. For example, in the last video, we found that the recurrence relation of merge sort is t of n equal to 2 times t of n by 2 plus n. And it matches the generic form because here a is 2, b is 2, and f of n is n. And by using the master theorem, we will be able to directly deduce the time complexity. When dividing a problem into subproblems, like we do in merge sort, we have 3 costs. We have the cost of solving the subproblems, the cost of splitting into subproblems, and the cost of combining results. Let's consider the cost of splitting and combining as one cost, and we will compare these 2 costs to deduce the time complexity. This is why the master theorem has 3 cases, when the first one is greater than the second one, when they are comparable, and when the second one is greater. First thing to do is to find the values of a, b, log b of a, and c. Here is a, here is b, log b of a can be calculated, and to find c we write f of n in form theta of n power c and you take the value of c. We will see it in examples. Now that we have these values, we compare log b of a with c, and if c is smaller than log b of a, then the time complexity is theta of n power log b of a. Else if they are equal, then the time complexity is theta of n power c times log n. Else if c is greater than log b of a, then the time complexity is theta of f of n. But this one is the basic version of the master theorem. We have the extended version that covers the cases where f of n is of type n power c times log n power d. The first case doesn't change, but in the second case, we need to check the value of d. If d is greater than -1, then the time complexity is theta of n power c times log n power d plus 1. Else if d is equal to -1, then the time complexity is theta of n power c times log n. Else if d is smaller than -1, then the time complexity is theta of n power c. And for the third case, if d is greater than or equal to 0, then the time complexity is theta of n power c times log n power d. Else if it's smaller, then the time complexity is theta of n power c. Oh, and by the way, we assume that the time complexity of the base case is constant. Enough theory, let's move to examples. Let's start with binary search. T of n is equal to t of n divided by 2 plus 1. And we can write it as a times t of n divided by b plus f of n. Here a is 1 and b is 2. Log b of a is log 2 of 1, which is 0. F of n is 1, which is n power 0, so c is equal to 0. Here log b of a is equal to c, so we are in the second case of the master theorem. We deduce that the time complexity of binary search is theta of n power c log n. We replace c by 0 and we get theta of n power 0 log n, which is theta of log n. Second example, factorial. T of n is equal to t of n minus 1 plus 1. Here we can't apply the master method because there does not exist a value b such that n divided by b is equal to n minus 1, so our recurrence relation doesn't follow the generic form of the master method. Third example, merge sort. The recurrence relation is t of n is equal to 2 times t of n divided by 2 plus n, and it follows the generic form. Here a is 2 and b is 2. Log b of a is log 2 of 2, which is 1, and f of n is n, which is n power 1, so c is equal to 1. Here log b of a is equal to c, so we are in the second case. We deduce that the time complexity of merge sort is theta of n power 1 log n, which is theta of n log n. Okay, we've seen some examples, and now I'll give you some recurrence relations, and the goal is to find the time complexity by using the Marston method by precising the case, and if the Marston method can be applied, just write that it can be applied. Take your pen and paper or software or something, and here are the recurrence relations. First example, 3 times t of n divided by 2 plus n squared. Here a is 3, b is 2, log b of a is log 2 of 3, which is around 1.58, and c is 2. 1.58 is smaller than 2, so we're in the third case. The time complexity is theta of n squared. Example number 2, a is 4, b is 2, log b of a is log 2 of 4, which is 2, and c is 2. 2 is equal to 2, so we are in the second case. The time complexity is theta of n squared log n. Example 3, a is 8, b is 2, log b of a is log 2 of 8, which is 3, and c is 2. 3 is greater than 2, so we are in the first case. The time complexity is theta of n cubed. Example number 4, a is 8, b is 2, log b of a is log 2 of 8, which is 3, and c is 4. 3 is smaller than 4, so we are in the third case. The time complexity is theta of n power 4. Example number 5, here a is not a constant, so we can't apply the Marston theorem. Example number 6, here a is smaller than 1, we can't have less than 1 subproblem, so we can't apply the Marston theorem. Example number 7, here the recurrence relation doesn't follow the required generic form, so we can't apply the Marston theorem. Example number 8, 2 times t of n divided by 2 plus n log n. Here a is 2, b is 2, log b of a is 1, c is 1, and d is 1. Log b of a is equal to c, so we're in the second case, and now we need to check the value of d. Here the value of d is greater than minus 1, so the time complexity is theta of n log n squared. Next example, 2 times t of n divided by 2 plus n divided by log n. Here we also have log. Know that in mathematics, a divided by b is a times b power minus 1, so here n divided by log n is equal to n times log n power minus 1. A is 2, b is 2, log b of a is 1, c is 1, and d is minus 1. Log b of a is equal to c, so we check the value of d. Here it's equal to minus 1, so the time complexity is theta of n log n. Next example, 4 times t of n divided by 2 plus n squared divided by log n squared. N squared divided by log n squared is equal to n squared times log n power minus 2. A is 4, b is 2, log b of a is 2, c is 2, and d is minus 2. Log b of a is equal to c, so we are in the second case. We have a look at the value of d. D is smaller than minus 1, so the time complexity is theta of n squared. Next example, 2 times t of minus n divided by 2 plus n cubed. Here a is 2, b is equal to minus 1/2, which is negative, so we cannot apply the Marston theorem. Next example, a is square root of n, so it's not a constant, then we cannot apply the Marston theorem. Next example, a is 4, b is 3, but f of n is minus n squared, which is not a non-negative asymptotic function, so we cannot apply the Marston theorem. Next example, t of n divided by 10 plus log n. Here a is 1, b is 10, log b of a is log 10 of 1, which is 0, c is 0, and d is 1. 0 is equal to 0, so we are in the second case, and d is greater than minus 1, so the time complexity is theta of log n squared. Next example, 2 times t of n divided by 4 plus square root of n. Note that in mathematics, square root of n is equal to n power 1/2. Here a is 2, b is 4, log b of a is log 4 of 2, which is 1/2, and c is 1/2. Log b of a is equal to c, so the time complexity is theta of square root of n times log n. Next example, 2 times t of n divided by 2 plus 2 power n. Here a is 2, b is 2, log b of a is 1, but we can't directly get the value of c. But you have to know that 2 power n is asymptotically greater than n power c, even if c is really huge. So we can, for example, put n power 1000 and 1000 is greater than 1, so we are in the first case. The time complexity is theta of 2 power n. Last example, a is 1, b is 2, log b of a is 0, c is 1, so we are in the third case. But here we can't apply the Marston theorem because f of n doesn't respect the regularity condition. Let me explain. The regularity condition says that for large values of n, a times f of n divided by b must always be smaller than or equal to k times f of n, where k is smaller than 1. In other words, the work done in the root must be greater than the work done in the leaf. In our case, a times f of n divided by b is n divided by 2 times 2 minus cos n divided by 2, and k times f of n is k times n times 2 minus cosinus of n. Let's represent graphically these two functions while replacing k with different values that are smaller than 1. With k equal to 0.1, k times f of n is smaller. With 0.5, we have cases where it's greater but not always. With 0.9, same thing. And by continuing like that, we find that the smallest value of k such that k times f of n is always greater is 1.5, which is not smaller than 1, so the regularity condition is not respected. And because the regularity condition is a necessary condition for the third case of the Mercer theorem, then we cannot apply the Mercer theorem for this example. We reached the end of this video. I hope that you understood the Mercer theorem and how to use it to measure the complexity of a recursive algorithm. Ask me questions if you didn't understand something, and see you in the next video. Welcome to this new video where we will learn how to measure the space complexity of a recursive function. Before talking about how to do so, we need to understand why is analyzing the space complexity of a recursive function different from analyzing its time complexity. Because we may think that to analyze the space complexity, we can just apply the same technique that we did with time complexity, getting the sum of operations performed by all the recursive calls by using the recursion tree method, the reconciliation method, or the Mercer theorem method. But you have to know that unlike time, we can free the space we aren't using anymore, so the amount of extra space can decrease. This is why the space complexity of a function is not the total amount of allocated extra space, it's the maximum amount of space that the function needed at a specific point of the process. Let me explain. Let's suppose that we have this non-recursive function. Here we create a list of n elements, we traverse it, we clear it, we create a list of m elements, we traverse it, and we clear it. In terms of time, we traverse a list of n elements, then a list of m elements, so the time complexity is O of n plus m. But in terms of space, we created a list of n elements, then we cleared it, then we created a list of m elements, then we cleared it. This means that the two lists weren't in memory at the same time, so we don't need m plus m extra space, we just need the max between n and m, so the space complexity is O of max between n and m. In relief, if for example this graph represents the extra space usage of a function at different moments of the process, then the required extra space is this one, not the sum. Now that you understood this, you have to understand when do we allocate memory in a recursive process and when do we free memory. We allocate memory when we create a new stack frame in the call stack and when we create a local variable in a recursive call. And we free memory when we finish a recursive call, we delete its stack frame and all the local variables. Okay, let's see an example to better understand. Let's analyze the space complexity of merge sort. We have two things to take into consideration, the call stack size and the sum of sizes of local variables. In merge sort, we need extra space to create the left part and the right part, because slicing an array creates a new one. If the array has n elements, the left part will have n by 2 elements, and same thing for the right part. And n by 2 plus n by 2 is n, so a recursive call that stores n elements requires n extra space. If we want to sort this array, for example, the initial function call will use n extra space, then it calls the function again to sort the left part. The n extra space is still in memory, and now we will sort the left part. Sorting the left part means that we will sort n by 2 of the array, which means that this call will need n by 2 extra space, and it calls again to sort the left part. And so on until we reach the base case. The base case directly returns r, it doesn't use extra space except for the stack frame. Same thing from the right, it directly returns r. And now that we got both parts sorted, we will join them and return the result. And as said earlier, when we finish a recursive call, its local variables get deleted, and same thing for its stack frame. Now we go to the right, and this call needs extra space, but you can see that it took the previous amount of space that we used for the left part without increasing the maximum amount of extra space for this process. And this process will continue like this until the end. From what we've seen now, we deduce that the maximum amount of extra space is the maximum call stack size plus the total size of local variables of one branch from the recursion tree. The maximum call stack size is represented by the number of levels of the recursion tree. In merge sort, the maximum total size of local variables of one branch is n plus n by 2 plus n by 4 and so on until 1. Because the initial function call uses n extra space, then the call that sorts the left part uses n by 2 extra space, then n by 4 and so on. This sum can be simplified to 2n minus 1. And we also know that the number of levels of the recursion tree of merge sort is log 2 of n plus 1, so the maximum call stack size is log 2 of n plus 1. We remove constants, we remove smaller terms, and we get a space complexity of O of n. What we did here is that we did the sum of sizes of local variables of the heaviest branch in the recursion tree plus the call stack size in that branch. By heaviest, I mean the branch that needs the greatest amount of extra space, even though in the recursion tree we've seen now all branches use the same amount. In Brief, to get the space complexity of a recursive function, we calculate the sum of sizes of local variables of the heaviest branch in the recursion tree plus its call stack size, and we simplify to get the space complexity. Now we use the recursion tree method, but we can also use the reconciliation method or the master method. Let's do it with merge sort. In the base case, we just return, so we write t of 0 is equal to 1, and in the recursive case, we need an extra space. But the difference with time is that, as said earlier, we free space after finishing a recursive call, so we calculate the space of one branch only, not all of them. This is why we write t of n is equal to t of n by 2 plus n, and not 2 times t of n by 2. We can use the master theorem method with this expression. Let's do it. A is 1, B is 2, log B of A is 0, C is 1, and D is 0, because n is theta of n power 1 times log n power 0. C is greater than log B of A, so we are in the third case of the master method. The space complexity is theta of n power C times log n power D, which is theta of n. Note that we have special cases. The first one is when all the recursive calls need the same amount of extra space. In that case, the general extra space required is the extra space required by one call times the maximum call stack size. We also have the case where a recursive call uses a constant amount of extra space. In that case, the space complexity is just the maximum call stack size because it's like we multiplied by 1. And we also have the case where we don't need to save stack frames because we don't need them. It's called tail recursion. In that case, the maximum call stack size is 1 because we only need one stack frame, the frame of the actual call. I hope that you understood how to analyze the space complexity of a recursive function. As always, don't hesitate to reach out if you have questions, and see you in the next one. Welcome to this new video where we'll talk about memoization. In the previous videos, we've seen the ways to climb stairs example, and if we have a look at the recursion tree, we can notice that there are repeated function calls that are doing the same work uselessly, which slows down a recursive process. And one of the ways to counter that is memoization. The idea of memoization is that every time we find the output of a recursive call, we store it in a lookup table so that the next time we need that value, we directly take it from there, without repeating the same work. In Brief, in the recursive call, we directly check the lookup map. If we already have computed the value, we directly return it. Else, we compute it, and before returning it, we store it in the lookup map. We have 4 steps to implement memoization on a recursive function. First step, add the lookup map as a parameter. The lookup map is a hash table where the key is the input of that call and the value is its output. And in Python, we use a dictionary. Second step, create the key of that call. The key of a recursive call is the concatenation of all its changing parameters separated by a space. For example, in ways to climb stairs, the only parameter that was changing is an, so the key contains an only. Third step, add a base case to check if we already have the value. We write if key in lookup map, return lookup of key. Last step, before every return statement, store the output in lookup of key, then return it. These steps are the general process to follow to implement memoization in a recursive function, but let's see an example on how to optimize the ways to climb stairs recursive function we've seen previously. Remember that we solved the problem recursively, but the problem is that we got repeated recursive calls. So let's see how the process works by adding a lookup map. The lookup map is empty at the beginning and n is 10 in the initial function call. 10 is not present in the lookup map, so we don't have the value, we have to compute it. Now we need the number of ways to climb to steps 8, 6, 5, and 2. Let's start with 8, and 8 is not present in the lookup map. 2 steps back gives 6, and 6 is not in the lookup map. 2 steps back is 4, and 4 is not in the lookup map. 4 minus 2 is 2, and 2 is not present. 2 minus 2 is 0, and n equal to 0 is the base case. But before returning 1, we store it in the lookup map and we return. Now 2 can't call with 2 minus 4, 5, or 8 because n would be negative, so the sum of ways to reach step 2 is 1. We store it in the lookup map and we return. Now 4 minus 4 is 0, and we know that it returns 1. The sum is 1 plus 1, which is 2, we store it in the lookup map and we return. Now 6 minus 4 is 2, and we already have it in the lookup map, so I will directly return 1. 6 minus 5 is 1, and we don't have it. 1 minus 2 is negative, same thing with 1 minus 4, 1 minus 5, and 1 minus 8. So we can't go to step 1, the number of ways is 0. We store it in the lookup map and we return. 6 minus 8 is negative, so the sum is 2 plus 1 plus 0, which is 3. We store it in the lookup map and we return. Now 8 minus 4 is 4, and we already have the value, it's 2. 8 minus 5 is 3, we don't have it. 3 minus 2 is 1, and we know that ways to reach 1 is 0. We can't perform any other call from 3 because n would be negative, so the sum is 0. We store it and we return. A minus 8 is 0, and we know that the output is 1. The sum is 3 plus 2 plus 0 plus 1, which is 6. We have 6 ways to reach step 8. We store and we return. Now 10 minus 4 is 6, and we already have the value. We directly return it. 10 minus 5 is 5, we don't have the value. 5 minus 2 is 3, we know that the output is 0. 5 minus 4 is 1, same thing, 0. 5 minus 5 is 0, base case, we get 1. 0 plus 1 is 1, we store and we return. 10 minus 8 is 2, and we have 2 in the lookup map. We know that we have one way to reach 2, so we return 1. 6 plus 3 plus 1 plus 1 is 11, and we got our output. We got that we have 11 ways to reach step 10 when the possible jumps are 2, 4, 5, and 8. And you can see that the recursion tree when we use memoization is smaller than the one when we didn't, which reduces the time complexity. Speaking of time complexity, let's see what gets reduced. Without memoization, we got a time complexity of O of n power n, but let's see what we get when applying memoization. Here we have two cases for recursive call. If it's the base case or we already computed the output before, then its time complexity is O of 1. Else if we don't have its value, except performing recursive calls, we have to traverse the n possible steps, so we have O of m. But here is the difference, the second case can happen only once for a value of n, because after it, we would have its value, no need to do the work again, so all the calls with that value after the first one will be O of 1. In our last example, the first time we needed ways to climb 4, we traversed the n possible steps and did the work, so the cost of splitting and combining is O of m. But all the calls with 4 after it didn't perform any recursive call, we had the value, they are O of 1. So in brief, the case where the function call needs to traverse the n possible steps can happen only once for a value of n. And now we need to know the number of keys where it enters the recursive case. In our case, n can't be below 0 because we have this condition. And n can't exceed its initial value because we are only subtracting, never adding to it. So the possible keys where it enters the recursive case go from 1 to n inclusive, which means that the number of keys is n. In other words, the number of calls that have to traverse the n possible steps can't exceed n. Now we just have to multiply by m and we get n times m, which gives a time complexity of O of n times m, which is asymptotically smaller than O of n power n. So we could optimize our solution through memoization. Now let's move to the code. We just have to apply those 4 steps. We add a parameter lookup, which is an empty map at the beginning. We create the key, which is just n in our case because we have only one changing parameter. And third step, we add the base case to check if we already have the value. We write if key in lookup, return lookup of key. And last step, before every return statement, except the first one obviously, we store the output in lookup of key and we return it. Note that if we have multiple changing parameters, for example I and g, the key would be a concatenation of all of them separated by a space. Conclusion, memoization is an optimization technique for recursive functions where we have repeated function calls. It operates by using a lookup map that saves values we computed before to avoid recomputing them later, and it reduces time complexity. Last two things, before moving to the next video. First of all, the lookup map is storing values, so it's using extra space. We have to check if it's impacting the space complexity. In our last example, the lookup map was using space to store the values of n keys, so the extra space uses n. But it didn't impact the space complexity because it was already O of n. Second thing, not all the recursive functions need memoization. Memoization has impact only when we have repeated function calls. In other terms, when we have overlapping subproblems. For example, when traversing a tree, memoization doesn't optimize anything because each node is unique, so each function call is unique. I hope that you understood memoization and how to use it. See you in the next video. Welcome to this new video where we'll talk about dynamic programming. Dynamic programming is another technique that we can use to optimize recursive solutions, but this time we won't keep the same solution and add things to it as we did with memoization. With dynamic programming, we will change the whole solution. We won't even use recursion. The core idea of dynamic programming is to find a relation between subproblems, then to always compute the next value starting from the ones we already computed. And dynamic programming works only when you can get an optimal solution from optimal solutions of smaller instances of the same problem. We say that the problem has an optimal substructure. You also have to know that dynamic programming has a noticeable impact on the time complexity of a recursive solution only when subproblems are overlapping. In other words, when we have repeated recursive calls. Let me show you an example. We want to use dynamic programming to calculate the nth term of the Fibonacci sequence. Reminder, the Fibonacci sequence is defined as follows. U0 is 0, U1 is 1, and Un is Un-1 plus Un-2. Let's verify the two conditions. Here, to calculate the term n, we can calculate the term n-1 and the term n-2 and do the sum, so we can divide the problem into smaller subproblems. Second condition, let's see if subproblems overlap. To calculate Un, we need Un-1 and Un-2. And to calculate Un-1, we need Un-2 and Un-3. You can see that we already found Un-2 twice, so we have overlapping subproblems. Now the idea to apply dynamic programming is to use tabulation. We create an array dp of n plus 1 elements, where the element at index I represents ui. N plus 1 because we want to get the nth term of the Fibonacci sequence, so the last index is n and terms start at 0, so we need n plus 1 elements. Now we already have the term 0 and the term 1, it's 0 and 1 respectively. Now for each remaining index, we can get its value by calculating the sum of the two previous elements, because Un is Un-1 plus Un-2. So dp of I is dp of I-1 plus dp of I-2. And after filling the table, the nth term is in dp of n, so we return it. Let's apply this logic for n equal to 8 for example. We create an array dp of 8 plus 1 elements, 9, we fill the first two elements, and we start. The first two elements in our case represent the base case, because in the recursive function, the base case is when n is equal to 0 to 1. Okay, now dp of 2 is equal to dp of 1 plus dp of 0, which is 1 plus 0, which is 2. Next element, dp of 3 is equal to dp of 2 plus dp of 1, 1 plus 1, 2. Next term, dp of 4 is 2 plus 1, 3. Next term, dp of 5 is 3 plus 2, 5. Next term, dp of 6 is 5 plus 3, 8. Next term, dp of 7 is 8 plus 5, 13. Last term, the one we're searching for, is 13 plus 8, 21. And we got the value of the 8th term of the Fibonacci sequence, which is 21. And you can see that we could solve it in all of one time complexity thanks to dynamic programming. You can also notice that this function is iterative, not recursive. Here we use the 1D array, but it's not always the case. We have problems where we need a matrix. For example, the longest common subsequence problem. The problem says that we have two strings str1 and str2, and we have to find their longest common subsequence. In this problem, we need to use a matrix of n plus 1 rows and n plus 1 columns, where n is the length of str1 and m is the length of str2. Then after filling it, we can find the length of their LCS in the bottom right cell. You have to know that the dynamic programming solution is a bit harder to find than the one that uses memoization, because you gotta figure out a way to turn your recursive solution into an iterative one that uses dynamic programming. But you'll become better at it by practicing. Now let's move to optimizing the ways to climb stairs solution by using dynamic programming. First of all, let's check the conditions. We know that the problem can be divided into smaller similar subproblems and that we have overlapping subproblems, so conditions are verified. The smallest value of n is 0, the base case, and the one we're searching for is ways to climb n stairs, so the idea is to create an array of n plus 1 elements where the element at the index I represents the number of ways to jump to the step I. We know that we have one way to jump to the step 0 is the base case, so we put 1. And now, for each remaining index, we do the sum of ways to jump to all the steps that can reach the step I, and we put it in dp of I. After it, the ways to climb to the step n is in dp of n, we return it. Let's do it with this example, n equal to 10 and possible steps are 2, 4, 5, and 8. We create an array dp of 10 plus 1 elements, 11, and we put 1 in dp of 0. Now we calculate dp of 1, 1 minus 2 is negative, same thing for 1 minus 4, 1 minus 5, and 1 minus 8, so the sum is 0, we have no way to reach step 1. dp of 2 now, dp of 2 minus 2 is 1, and other possibilities are negative, so the sum is 1. Now dp of 3 minus 2 is 0, and other possibilities are negative, so the sum is 0. dp of 4 now, we can get dp of 4 minus 2 and dp of 4 minus 4, both of them are 1, the sum is 2. For dp of 5, we have dp of 3 equal to 0, dp of 1 equal to 0, and dp of 0 equal to 1, the sum is 1. dp of 6, we have dp of 4 equal to 2, dp of 2 equal to 1, and dp of 1 equal to 0, the sum is 3. dp of 7, we have 1 plus 0 plus 1, we get 2. dp of 8, we have 3 plus 2 plus 0 plus 1, the sum is 6. dp of 9, we have 2 plus 1 plus 2 plus 0, the sum is 5. Last element, the one we're searching for, dp of 10 is equal to dp of 8 plus dp of 6 plus dp of 5 plus dp of 2, which is 6 plus 3 plus 1 plus 1, which gives 11. We have 11 ways to reach the step 10. Now for the time complexity, we are traversing n elements in the array, and at each iteration we are traversing the n possible steps, so we have n times m. We get a time complexity of n times m, which is asymptotically better than the complexity of the non-optimized recursive solution. Last thing that I want to talk about is top-down and bottom-up approaches. In memoization, with this example, we want to calculate ways of 10, so we calculate ways of 8, ways of 6, ways of 5, and ways of 2. And to calculate ways of 8, we calculate ways of 6, ways of 4, ways of 3, and ways of 0, and so on. So we start at the initial value of n, which is 10, and we keep recurring until we reach the base case, which is 0. This is what we call a top-down approach. We start from the top and we go down. But in dynamic programming, by using tabulation, we start from the base case, which is n equal to 0, and we keep generating the next values until we reach the initial value of n, which is 10. This is what we call a bottom-up approach. We start from the bottom and we go up. In brief, memoization follows a top-down approach and tabulation follows a bottom-up approach. I hope that you now know a little bit about memoization and dynamic programming. Ask me questions if you didn't understand something, and see you in the next video. Welcome to this new video where we will see the difference between recursion and iteration. First of all, what is iteration? Iteration in programming means repeating the same process multiple times, which is usually done by using a loop. A lot of people say that recursion is just an alternative to iteration, but I think that it's wrong. Yes, we can convert any recursive function to an iterative one and vice versa, but we have cases where it's more intuitive to use iteration and cases where it's more intuitive to use recursion, so it's better to know both and more especially when to use one over another. Recursion is usually a better choice in situations where the problem can be divided into smaller instances of the same problem. For example, to sort an array by using merge sort, we merge sort the left part, we merge sort the right part, and we join the sorted arrays. So here we divided the merge sort problem into two instances of the same problem, applying merge sort on the left part and on the right part. We can implement this process iteratively, and I'll show you how to do so in the next video, but you can see that it's more intuitive to use recursion here. Second example, ways to climb stairs. To find the number of ways to climb n stairs, we have to get the sum of ways to climb to all the steps that can reach the last step. Again here, we divided the problem into multiple subproblems of the same type. It's more intuitive to use recursion. Last example, binary search. To perform binary search, if the element we're searching for is equal to the element in the middle, it means that we found it. Else if it's greater, we apply binary search on the right part, else if it's smaller, we apply binary search on the left part. Here we have only one recursive call, but we're using a smaller input at every call, so we can say that we divided it into a smaller subproblem, and it's more intuitive to use recursion here. And for iteration, it's more intuitive to use it when we want to repeat the same process many times, or when we want to traverse the elements of a linear data structure like an array or a string or something like that. Before ending this video, let me tell you two things about using recursion over iteration. First thing, you have to be very careful when writing the recursive function, because if something doesn't work, you can have a stack overflow caused by an infinite recursion. This case happens when the base case is never reached. For example, in ways to climb stairs, the condition that prevented infinite recursion is this condition. Before calling the function, we made sure that n is positive because we don't have a base case that handles the case where n is negative. So if we didn't add this condition and n becomes negative, it doesn't stop. It keeps calling the function again with negative values until the infinity. Note that we could use this base case instead of the condition and things would work properly. Or for example in merge sort, if we decide to stop only when R has 0 elements and not 1, the recursion would never stop, because when we reach the case where R has 1 element, it will call the function twice. Once with the empty array, this one will stop because the length is 0, and once with an array of 1 element, and same problem again, it won't stop. All that because dividing an array of 1 element into 2 parts will give you an array of 0 elements and an array of 1 element, again and again. This is why it never stops. Second thing, repeated function calls. As said in a previous video, we can have repeated function calls where we do the work again uselessly, like with the recursive implementation of the Fibonacci sequence. And to counter this, we can use either memoization or tabulation. We will see both of them in the next chapter. In other words, if you notice that your recursive function is doing the same work many times because of repeated function calls, try to apply memoization or tabulation to reduce time complexity. I hope that you now know the difference between recursion and iteration and when to use one over another, and see you in the next video. Welcome to this new video where we will see how to transform a recursive function into an iterative one. We said that in recursion we have a call stack that stores the different active recursive calls. It gives us the ability to navigate between the calls while storing the parameters, the local variables, and all that stuff. This is why when transforming a recursive function into an iterative one, we usually create a stack that will act as the call stack, and as said earlier, when we have a new function call, we push onto the stack. So the idea is to create a stack, then keep looping while the stack isn't empty. But we have a problem. As you may know, in recursion, when we have a recursive call, the function stops, the recursive call gets executed, then we go back to resume the initial call. But in iteration, we can't do that directly. We can't just stop an iteration and start another one, then backtrack to the previous one. So the method that I use is to use 2 stack frames for each call, one to perform instructions before the recursive calls, and one to perform instructions after the recursive calls. So in our stack frame, we will add a parameter that can take the value start or resume. It will let us know if we call the function for the first time or if we are resuming it. Let me give you an example. We have a binary tree and we want to print its node in a post-order traversal. The post-order traversal is a depth-first traversal where we print the left subtree, we print the right subtree, then we print the node's value. So the recursive function would look like this. You can see that before recursive calls, we checked if we are in the base case, and in the recursive case, we called the function with the left node, then the function with the right node, and after the recursive calls, we print the node's value. So in our iterative function, we create a stack and we pass a tuple that contains the action and the tree's root. Here the action is start because we will call the function, not resume it. Now, while the stack is not empty, we have the case where the action is start and where the action is resume. In the start part, we execute instructions before recursive calls, and in the resume part, we execute instructions after recursive calls. But before, we first unpack the tuple to get the action and the node. Okay, now in the start part, we first check if it's the base case. If it's the case, we do nothing, we just pass. Be careful, we don't return like in the recursive function, because here we have only one function call. Else if it's the recursive case, we have to push a new frame for the call on the left subtree and one for the right subtree. But don't forget that we need to resume this call, so we also have to push a frame where the action is resumed, and we do it before others because the stack works on the FILO principle, first in last out, so the first stack frame pushed onto the call stack gets executed at the end, which is what we want here. We want to resume this call after executing the recursive calls on subtrees. Now we push one frame for the left child and one for the right child. The action is of type start because it is the first time that we will enter the call. And in the resume part, we just print the node's value, and we got our iterative function that prints a binary tree in post order. And you can see that all the math that we created could be easily done recursively, and the call stack would handle all the stuff. This is why I told you that some algorithms are recursive by nature, and trying to convert them into an iterative function will just give you the responsibility of having to handle the call stack. but the idea of the process remains the same. But we have some exceptions, obviously. And things get worse when we need to return a value to the previous call, because another problem is that the loop iteration can't directly return a value. The idea that I found is to use variables that can be changed from elsewhere, an array for example. Let's take as an example an iterative function to get the sum of elements of a binary tree. In the recursive function, if the tree is empty, we return 0. Else, we get the sum of the left subtree, we get the sum of the right subtree, and we return node's value plus left sum plus right sum. That's it. The idea that I got to convert this recursive function into an iterative one is to use a stack where a stack frame contains the action, the node, the variable where to put the returned value, the variable to pass to get the sum of the left subtree, and the variable to pass to get the right subtree. In code, we create a stack, we create output, which is an array of one element where the initial stack frame will put its returned value, and we push the first frame. I'll say it again, I use an array of one element instead of a simple variable to be able to modify it from elsewhere later. Now inside the loop, we unpack everything and we check if the action is start or resume. If it's start, we check the base case. If the tree is empty, we just return 0. But here, instead of using the return statement, we have to put 0 in the variable where we are asked to put the output of this stack frame, which is ret of 0. Ret of 0 because it's an array of one element. Else if it's the recursive case, here you have to follow well. We will do what we did with the previous example. We first push a frame to resume the actual one later, and we push a frame for the left subtree and one for the right subtree. But look at the parameters we passed here. We said that the first parameter is the action. To resume, we write resume, and to start a new call, we write start. Then the second parameter is the node. We want to resume with the same node, so we just write node. But for the left subtree, we pass node.left, and for the right subtree, we pass node.right. Third parameter, the variable where we put the output of the frame. When resuming, we just pass the same one, ret. But with the left subtree, we want to put its output in the sum of the left subtree of the actual node, so the output must be in left. Same logic for the right subtree, we want to put its output in the sum of the right subtree of the actual node, so we pass right. Fourth and fifth parameters, the sum of left and right subtree respectively. When resuming, we continue the actual ones, so we pass left and right. But for the subtrees, we create new ones. This is why we pass a new array of one element for each. And when resuming the call, we have to return the sum, but as said earlier, we don't use the return statement. We have to put the output where we are supposed to, ret of 0. So ret of 0 becomes equal to the node's value plus the sum of the left subtree, which is left of 0, plus the sum of the right subtree, which is right of 0. And after finishing all the process, the output, which represents the sum of the whole tree, is actually an output of 0, so we return it. Here is how this function works for this binary tree. Before ending this video, you have to know two things. When converting a recursive solution into an iterative one, it's not always a mess like here, because we can have cases where you don't need to go back to the previous calls. This is why we can just use a loop like with the factorial example, and we will talk about why we don't need to go back more in depth in the chapter about recursion. Or we can mention the iterative method to perform merge sort without using a stack. I hope that you understood the concepts presented in this video. Ask me if you didn't understand something, and see you in the next one. Welcome to this new video where we will see how to transform an iterative function into a recursive one. In an iterative function, we usually have local variables, then a loop, then the return statement. To turn it into a recursive function, we put the local variables as parameters, the loop condition break as the base case condition, the return statement inside the base case, and the body of the loop as the recursive case. Let's see an example. We want to get the number of divisors of a strictly positive integer n. For example, 12 has 6 divisors, 1, 2, 3, 4, 6, and 12. We can know if b divides a by checking if a mod b is equal to 0. And what we're gonna do in our iterative function is that we will loop over integers from 1 to n, and if n mod I is equal to 0, we increment count. It means that we found a new divisor. We can do it with the while loop or with the for loop. Let's start with the while loop. We have count equal to 0, I equal to 1, then while I is smaller than or equal to n, if n mod I is equal to 0, we increment count, and we don't forget to increment I to move to the next integer. After the loop, we return count. Now, to turn it into a recursive function, local variables, which are count and I, become parameters whose default values 0 and 1 respectively. Now for the base case, we put the loop break condition. Here the loop keeps running while I is smaller than or equal to n, so it stops when I becomes greater than n. This is why we write if I is greater than n. And inside the base case, we put what comes after the loop, in our case, return count. And in the recursive case, we write what's inside the loop, and we don't forget to return the recursive call with the same parameters to move to the next iteration. So this recursive function will keep running until I exceeds n, where it returns count. Let's do it now with the for loop iteratively. This is what the function would look like. We've put n plus 1 because the n parameter is exclusive, so we have to put the successor of the last value that I can take, which is n. In recursion, same logic. Local variables become extra parameters with default values initial value, the loop break condition becomes the base case condition, what comes after the loop becomes the base case, the loop body becomes the recursive case, and when calling the function again, we don't forget to add 1 to I, because the incrementation is done implicitly by the for loop, so we don't forget to do it when calling again. Or you can just write I plus equal 1 like with the while loop, both methods work. And obviously, here we added 1 because I increases by 1 at every iteration. So for example, if I were increasing by 2, we write I plus 2. We can also use this technique to traverse an array or string recursively. For example, we want to get the minimum value from an array. Iteratively, we could write this. And recursively, local variables are I, the index, and minval. They become extra parameters. The base case is when I reaches the length of R. It means that we traversed all the elements. We write, if I is equal to length of R, we return minval. Else in the recursive case, we check if the element at index I is smaller than min, then we return the function again with I plus 1. I plus 1 for the same reason as the last example. Note that if we have an early exit return, we add it as a base case in recursion. For example, we have an array and we want to check if the value val is in it. Iteratively, we would write this. Inside the loop, if r of I is equal to val, we darkly return true. We don't check the remaining elements. So in recursion, we write if I is equal to length of r, we return false. It means that we didn't find val. Second base case, if r of I is equal to val, we return true. And in the recursive case, we have nothing to do because we already checked if r of I was equal to val, so we just return the function call with I plus 1. Oh, and by the way, when transforming an iterative function to a recursive one, we get a tail recursive function. We will talk about that in the chapter about tail recursion. See you in the next video. Welcome to this new video where we will talk about divide and conquer. Divide and conquer is an algorithm technique that is often implemented by using recursion. Divide and conquer works by dividing the problem into non-overlapping smaller instances of the same problem, solving them, then combining the results. So it has 3 steps: divide, conquer, and combine. In reality, we've already seen in this course algorithms that use divide and conquer, like merge sort. Merge sort divides the array into 2 halves, sorts them, then joins them into a sorted array. And divide and conquer algorithms usually work recursively, because when it divides the original input, as we did in merge sort, it then divides the parts again and again until it reaches very small instances of the problem that are easy to solve directly. In merge sort, for example, it's when the array has at most one element, where we directly return it because it's already sorted. And the last step is to combine results returned by the subproblems, because our goal is to get one result, so we have to find a way to produce it starting from the results that we got from our subproblems. In merge sort case, we got both parts sorted, and to join them into the result we're searching for, which is the original array sorted, we join them into a sorted array by always comparing the next element of both parts and taking the smaller one. Applying divide and conquer can also give us a solution that is more optimized than the brute force solution. For example, when multiplying two large n-digit integers x and y, if we apply the naive method that we learned in school, we'd get a time complexity of O of n squared. But by applying the Karatsuba algorithm, we get a time complexity of O of n power log 2 of 3, which is O of n power 1.59. To perform the multiplication of two n-digit integers x and y, we first divide x into two parts a and b, we divide y into two parts c and d, we calculate a times c by using the same function, we calculate b times d by using the same function, and now we need to calculate ad plus bc. ad plus bc is equal to a plus b times c plus d minus ac minus bd. We already calculated ac and bd, and for a plus b times c plus d, we just use the recursive function we're defining. And now, to get x times y, we return ac times 10 power 2 times an Euclidean division by 2 plus ad plus bc times 10 power an Euclidean division by 2 plus bd. Note that n represents the maximum number of digits among x and y. And this is a recursive function, so to calculate ac for example, we perform the same process until we reach the base case where one of the parameters has only one digit. In that case, we just perform the multiplication normally. Here is the recursion tree for this example. In the two previous divide and conquer examples, merge sort and Karatsuba, we had two or more recursive calls. This is why we had to combine results after solving subproblems. But note that we can have an algorithm that uses divide and conquer but has only one recursive call. An example of that is binary search. As said previously, binary search performs only one recursive call to continue searching on the part where the search value can be, left one or right one. This means that we have nothing to combine after the recursive call, we already have the result. And when we use divide and conquer to divide a problem into exactly one smaller instance of the same problem, we usually call it decrease and conquer, because we decrease the input size. For example, in binary search, initially we have to search among n elements, then n by 2 in the next call, then n by 4, and so on. Now I want to end this video on the advantages of divide and conquer. Three important advantages of the divide and conquer method are: first one, simplifying complex problems. Because divide and conquer can help us break down a problem into small pieces that are easy enough to solve. Then, we just have to find a way to combine them. Second one, efficiency. Using divide and conquer can give us an algorithm that is more efficient than the classic method, as we've seen with the Karatsuba algorithm. Third one, parallelism. Dividing a problem into subproblems means that we have the possibility to solve each one of them separately. It's perfect for multiprocessor machines where each subproblem can be solved in a separate processor. It's like dividing the array into two parts in merge sort, then giving each part to a single person to sort it without needing each other. But don't forget that an algorithm that uses divide and conquer is often implemented recursively, so you have to be careful with choosing the right base cases and recursive cases, thinking about the call stack overflow and all that stuff that comes with using recursion. I hope that you now know a little bit about divide and conquer, and see you in the next video to talk about backtracking, another interesting recursive technique that you should know about. Welcome to this new video where we'll talk about backtracking, another algorithmic technique based on recursion. Backtracking works by trying to build a solution incrementally, and as soon as it finds out that the actual solution it's building is not valid, it backtracks to a previous point and tries another possibility. For example, when solving a maze by hand, what we usually do is to go from a particular path, actually called the candidate because it's a potential valid solution, then as soon as we find a wall that blocks our path, it means that this path cannot take us to the maze exit, so we backtrack. We go back to the previous point that still has other possibilities, and we try another one. Then again, if we find ourselves blocked, we backtrack again and try another possibility. And so on until the end. Then, if we find a solution, we have two choices. We can either stop. We do that when we just want to know if a solution exists, in this example if a valid path exists, or we can continue checking other possibilities. We do that when we want, for example, to get all the valid solutions, in this example all the valid paths. Okay, let's see an example. We have a knapsack that can contain max weight kilograms, and we have an array weights where weights of I represents the weight of the item I, and we want to get all the possible combinations of items that we can take whose total sum doesn't exceed max weight. For example, if we have this input, a possible combination is to take items 0 and 2, the total weight is 6, it doesn't exceed max weight, so it's a valid combination. We want the output to be an array that contains all the valid combinations. And the idea to solve this problem by using backtracking is that for each item I, we call the function again twice, once by taking the item and subtracting its weight from the remaining possible weight, and once by not taking it. And if the remaining weight becomes negative, it means that the actual combination exceeded the max weight, which means that it's not a valid combination, so we directly backtrack and continue searching from elsewhere. And if we reach the end of the weights array and the remaining weight is not negative, it means that we found a valid combination, so we add it to our output array. But we continue searching because we want to find all valid solutions, not just one. Okay, let's apply this process for this example. Note that comp array contains the actual combination and comps array contains all the valid combinations, and they both start empty obviously. Next thing to know is that a function call takes 5 parameters: the weights array, max weight, I, comp, and comps. But in the recursion tree, I'm putting only I and max weight. You can see the actual state of remaining parameters at the bottom. Let's start. The initial call starts at the first item, so I is 0 and max weight is still 7. Now we search possible combinations when taking the item 0, so we append it to comp and subtract its weight from max weight. You can see that in this new recursive call, max weight became 3 because we subtracted 4, which is the weight of the item 0, from 7. In other words, the second parameter is representing the remaining weight. Now we search when we also take the item 1, so we subtract 7, its weight. Here you can see that max weight became negative, so this combination is not valid because 4 plus 7 exceeds the initial max weight, so we backtrack and we remove item 1 from our comp. Now we try by not taking item 1, so max weight doesn't change, because we didn't take the item. Now let's try taking item 2, we subtract 2, remaining weight became 1, but it's not negative, so it's fine. Let's try taking item 3, we subtract 1, and now we traverse all the elements and the remaining weight is not negative, so we found a valid combination, we add it to our comps array. Here we found a solution, but we want to find them all, so we don't stop here, let's backtrack and continue. Now we try by not taking item 3, and we reach the end again and the remaining weight is not negative, so we found a new combination. We backtrack and here we backtrack again because we have nothing to do in this call anymore. Now we try by not taking item 2. If we take item 3, max weight becomes 2, valid, we take the combination. We backtrack and now we don't take item 3, the max weight remains positive, we take the combination. Now we backtrack and we backtrack again. Oh, by the way, if you want to understand a root to leaf path, know that going to the left means that we took the element and going to the right means that we didn't. Okay, let's continue. Now we don't take the item 0, so max weight remains 7 and comp remains empty. Now we take item 1, we don't forget to subtract its weight. Now we take item 2 and max weight becomes negative, so it's not a valid solution, we backtrack. Now we don't take item 2. Now if we take item 3, max weight becomes negative, so even if we reach the end of the array, we don't take the combination, because its total weight exceeds max weight, so we just backtrack. And if we don't take item 3, max weight remains 0 and it's fine, so we take the combination and we backtrack. Here we backtrack and we backtrack again. Now we don't take item 1. Now we take item 2. Now if we take item 3, max weight remains positive, so we add the combination. We backtrack, and if we don't, same thing, we add the combination and we backtrack. Now we backtrack and we don't take item 2. If we take item 3, positive, we add the comp and we backtrack, and when we don't, same thing, we add the comp and we backtrack. Now we backtrack again, and we finish traversing all the possibilities. We can find all the valid ones in comps array, so we just return comps. What we did here basically is that we traversed all the possibilities, and every time the actual possibility became non-valid, we directly abandoned it. We didn't continue. And when we reached the end of the weights array without exceeding max weight, we added the actual combination to the valid combinations. Okay, now what about the code? We need two functions here, a recursive function that will perform backtracking and a non-recursive function that will create comps array, call the recursive function to fill it, and return comps array. For the recursive function, we said that it takes 5 parameters, weight array, max weight, I, comp, and comps. Now we have two base cases, the negative base case, where we abandon the actual possibility, and the positive one, where we find out that the actual possibility is valid. The negative base case is when max weight becomes negative, we directly backtrack. Else, if we reach the end of weights array, in other words, when I becomes equal to length of weights, we append the copy of comp to comps. By the way, here the order of base cases is important, because if we switch them, the case where I is equal to length of weights but max weight is negative will be considered valid, which is not what we want. Okay, now in the recursive case, we try both possibilities, when we take the item I and when we don't. So we append the item to comp, we call the function with I plus 1, and now when we go back to this call, we have to remove it, because now we will do the case where we don't take the item I. This is why we pop, and we call the function again with I plus 1. I plus 1 is to move to the next item. You can see that this function is returning nothing, it's just filling comps array. This is why in the non-recursive function, we create an array comps, we call rec function to fill it, and we return it. And we finished writing this function that applies backtracking to this variant of the original knapsack problem. Note that the original knapsack problem is slightly different. Here, the logic that we followed is to traverse possibilities, then appending to the output array every time we find a valid solution. But we can also follow another logic. The logic of the second way to write a backtracking algorithm is that we get the valid possibilities when we start from the next index, we create our comps array, then for each valid combination from the next index, we add it to comp, and if its total weight plus the weight of the item I doesn't exceed max weight, we add the item I to comp and we append comp to comps array, which would mean that taking the actual item also gives a valid combination. In code, we have a base case where I is equal to weight's length, where we have no more remaining elements, so the only valid combination that we can make is the combination that has no elements, so we return an array that contains the empty combination. Else, in the recursive case, we get the valid combination starting from the next index, I plus 1. We create comps array, then for each comp in from next, we add it to comps because we already know that it's valid. And if the sum of weights of its items plus weights of I is smaller than or equal to max weight, it means that comp plus item I is also a valid combination, so we append I to comp and we append comp to comps. After the loop, comps now contains all the valid combinations when we start from the index I, so we return it. Another example of an algorithm that uses backtracking is DFS, depth first search, the one we use to traverse a tree or a graph. We start by diving deep into one branch, then as soon as we find a leaf, in other words, a node that has no children, it means that we can't continue further, so we backtrack and continue from another branch. And we keep doing this until we finish traversing the whole tree or graph. I hope that this lecture on backtracking was interesting and easy to understand. In the next one, we will see a classic backtracking problem, the n queens problem. See you there. Welcome to this new video where we will see the n queens problem. So what does the problem say? It says, given a positive integer n, create a function that returns the number of possible ways to put n queens on an n by n chessboard such that no two queens attack each other. Note that two queens attack each other when they are on the same row, column, or diagonal. I hope that you try to solve the problem, so let's start. Before jumping into the solution, here is a 4x4 chessboard. Pause the video and try to find one way to put 4 queens on it such that no two queens attack each other. If you tried, I think that the technique you used is that you put a queen on the first row, then you search for a valid spot in the second row, then in the third row, etc. A valid spot means that the queen is not attacked. For example, this one is not a valid spot because the queen is attacked. There is another one in the diagonal. Let's try to apply this method in detail. The chessboard starts empty obviously, and the idea is to get the number of possible ways when we put a queen on the first column, then on the second one, and so on. We start in the first row as said earlier, and we put a queen on the first column. The queen is not attacked, so we can move to the second row. If we put a queen on the first column, it will be attacked, so we remove it and we backtrack. Second column, same thing. But with the third column, the queen is safe, we can move to the third row. First column, attacked, we backtrack. Second column, same problem. If we put a queen on the third column, it will also be attacked, we backtrack. Fourth column, same problem. It means that when putting a queen in the third column of the second row of this chessboard, we have no way to continue because the queen on the third row will always be attacked, so we have to backtrack. Now we try with the last column, and it's not attacked, so we can move to the third row. We start with the first column, but it's attacked, we remove it. Second column, the queen is not attacked, so we can move to the last row. And if we find a safe spot in the last row, then we will have found a valid way to put 4 queens. First column, attacked. Second column, attacked. Third column, same thing. And last column, same thing. Unfortunately, we didn't find a safe spot for the last row, and we have to backtrack again here. We try with the third column now, but it's attacked, we backtrack. Last column, also attacked, we backtrack. We finished all columns of the third row, so we backtrack again. Same thing here, we tried with all columns of the second row, we backtrack again. Back to the original call, we have to try now by putting a queen on the second column of the first row, not the first one. We repeat the same process now. First column, attacked, we backtrack. Second column, also attacked. Third column, also attacked. Last column, not attacked, we can continue. We go to the third row. First column, not attacked, we can go to the last row. First column, attacked, we backtrack. Second column, same thing. But with the third column, we can put a queen without being attacked, and it's the last row, so we finally found a way to put 4 queens on a 4x4 chessboard. But we don't stop here because we want to count all the possible ways, so we backtrack and we continue. Last column, attacked. We finished all columns, we backtrack. Second column now, attacked, we backtrack. Third column, same problem, we backtrack. And last column, also attacked. We finished all columns, we backtrack. Same thing here, we backtrack. We did 50% of the work now, and here I'll just take the chessboard to the left side so that you can see the right part of the recursion tree. We put a queen on the third column now, and we move to the second row. First column, not attacked, we move to the third row. First column, attacked. Second column, also attacked. Third column, same thing. And last column, not attacked. We go to the last row. First column, attacked. But the second one is not attacked, and is the last row, so we found another way to put the 4 queens. We found 2 ways in total until now. We backtrack and we continue. Third column, attacked. And last one, same thing. Here we finish, so we backtrack, and same thing again here. Second column now, the queen is attacked, we backtrack. Third column, also attacked, and last one, same thing. We finish traversing all possibilities when we put the queen on the third column on the first row, so we backtrack, and we try with the fourth column. Second row now, first column, not attacked, let's go to the third row. First column, attacked. Second one, same thing. Third one, not attacked, we go to the last row. First column, attacked. Second one, same thing. Third one, same problem. And last one, also attacked. So we have nothing to do, we backtrack. Last column now, the queen is attacked, we backtrack. We checked all columns, we can backtrack. Second column now, it's safe, we can continue. First column, the queen is attacked. Second column, also attacked. And third one, same thing. So we backtrack. And last one, also attacked, so we can do nothing here, we backtrack. Third column now, it's attacked. And last column, also attacked, so we backtrack. We finished all columns, so we backtrack, and same thing here, we traversed all possibilities for the first row, so the function calls ends here. And here is the whole recursion tree. You can see that we found 2 ways to put the 4 queens, here are them, so the function returns 2. Note that here we represented the chessboard visually, but in code we will use an n by n matrix of characters, where an empty cell is represented by a point and a cell that contains a queen is represented by an uppercase Q. Before writing the main solution function, we have to know how to check if a queen is attacked or not. We said that a queen is attacked when there is another queen on the same row, column, or diagonal. Let's for example check if this queen is attacked. We are not putting 2 queens on the same row, so we don't have to check it. And we are filling the chessboard top to bottom, so we know that the part under our queen is still empty, which means that we just have to check the diagonal, the column, and the anti-diagonal from the top only. And in order to do that, let's put a variable I on the previous row, a variable gleft on the left column, and a variable gright on the right column. If you are wondering why did we do that, it's because at each row we have to check 3 cells, the one on the diagonal, the one on the column, and the one on the anti-diagonal. And they are all on the same row, the row I, so to get the cell on the diagonal we write board of I gleft. To get the cell on the column we write board of I col, where col is the column of our queen, and to get the cell on the anti-diagonal we write board I gright. After checking that those cells don't contain a queen, we have to move to the row before it to continue checking. So we decrement I, we decrement gleft to continue being on the diagonal, and we increment gright to continue being on the anti-diagonal. And we keep repeating this process until we have no more rows to check. In code, we first define the function, it takes the chessboard and row and col, which are the coordinates of our queen. Then we create our variables. I is initialized to row -1, gleft to col -1, and gright to col +1. Now we can start checking, and we have 3 situations where the queen is attacked, when board of I col is a queen, when board of I gleft is a queen, and when board of I gright is a queen. So if one of them is true, it means that our queen is attacked, so our function, which checks if the queen is not attacked, returns false. And by the way, we always check that gleft is greater than or equal to 0 and that gright is smaller than n to avoid going out of bounds. Else if there is no queen in our cells, then we have to update our variables to search in the previous row, so as said earlier, we decrement I, we decrement gleft, and we increment gright. After the loop, if the function didn't return false yet, it means that the queen is not attacked, so we return true. Now we can start writing our solution, and we start with the recursive function. It takes n, which is the number of queens, the chessboard, and the actual row, the one where we're gonna put the next queen. The base case of this recursive function is when the actual row is greater than or equal to n. It means that we arrive to the end of the chessboard. In other words, we've been able to put all queens without them being attacked. So we found a new way, this is why we return 1. And in the general case, we want to count the number of ways that we get by putting the queen on the first column, then on the second one, and so on. So we need the variable someways initialized to 0, and we will each time add to it the number of ways that we got by putting the queen on column I. Now, we need a for loop to iterate over columns, and at each iteration, we first check that by putting the queen it won't be attacked, by using the function we made. And the coordinates of the actual cell are row and I, so we call the function with parameters board, row, and I. And if the function returns true, it means that the cell is safe. In other words, we can put a queen and move to the next row. And it's what we do, we put a queen in board of row I, and we call the function again with row +1 as parameter to get the number of ways by starting from the next row with the actual configuration. And we add the result to our someways variable. After that, we have to remove our queen from the actual cell, as we were doing in the example when we were backtracking. After the loop, we will have got the number of ways that we can get with the actual configuration, so we return someways. Now in the main solution function, we just create an n by n matrix that represents the chessboard, where all cells are empty at the beginning, and we return the result returned by the recursive function by starting at row 0. The problem we've seen now is a classic backtracking problem, so if you understood it, then other backtracking problems will probably be easier for you now. Check the code below, ask questions if you didn't understand something, and see you in the next lecture. Welcome to this new video where we'll talk about the relation between recursion and linked lists. First of all, we need to talk about what is a recursive data type. A recursive data type is a data type that contains values of the same type as itself. For example, if we define a data type point that contains 2 attributes x and y of type int, then it's not a recursive data type, because it doesn't contain an attribute of type point. But if we write this, then point would be a recursive data type, because it contains an attribute of type point. It can, for example, represent the next point in a geometrical form or something. The first recursive data type that we will talk about is the linked list. It's a recursive data type because a linked list node contains a value that can be of any type and a reference to the next node. So this is what a linked list would look like. The last node of the linked list doesn't point to any node, so its next attribute is known. Linked list manipulations can also be done recursively. For example, if we want to print the linked list, we can write this. The recursive function takes a node from the linked list, then if it's null it means that we reach the end, so we do nothing. Else, we print the node's value and we call the function again with node.next to print the linked list that starts from the next node. Or for example, if we want to check if the linked list contains a specific value, we can also use a recursive function. If the node is null, it means that we reached the end of the list and we didn't find it, so we return false. Else if the node's value is equal to the one we're searching for, then we return true. Else, we just continue searching starting from the next node. Note that even if a linked list node is a recursive data type, we're not obliged to manipulate it recursively. The two functions we made now can also be done iteratively by using a while loop. I hope that you understood this lecture and see you in the next one. Welcome to this new video where we will talk about another recursive data structure, the tree. We've already seen the tree before. I told you that a tree is made of a value and reference to other trees that represent its children. And as you can see, the tree is a recursive data structure because its children are also of type tree. And the tree is the perfect data structure to practice recursion, because the main manipulation, which is traversing the tree, is usually done recursively by reading the actual node then traversing all its children. And by using this pattern, we can do many things. You want the sum of elements, calculate the sum of children recursively, then add the actual node's value and return. You want to get the maximum value, search for the maximum in each subtree while keeping track of the greatest one. You want to get the height of the tree, get the maximum height among children, and add 1 to count the actual level. Note that once again, you're not obliged to use recursion to manipulate a tree. Here we were using depth first search traversal, which is recursive by nature, but we could also use the breadth first search traversal that traverses the tree level by level. This one is usually done iteratively. I hope that you understood this lecture and see you in the next one. Welcome to this new video where we will talk about another recursive data structure, the graph. The graph is a collection of nodes and some of them are related by edges. A graph node is made of a value and references to other nodes, usually called neighbors. So it's a recursive data type. And traversing a graph is similar to traversing a tree. To traverse a graph in depth first search, we start from any node, we read its value, then we traverse its neighbors recursively. But a graph can contain cycles, which would cause an infinite recursion. So to avoid this, we use a set of visited nodes to be able to check if we didn't visit a node before. The graph is a really interesting data structure. It has a whole mathematics subfield named graph theory. You can almost represent any problem by using a graph, and there is a lot of things to know about them. I'm even thinking about making a course about it. We reached the end of this short chapter about recursive data structures. It's just to show you that understanding recursion will help you to manipulate recursive data structures like linked lists, trees, and graphs. As usual, if you have a question, don't hesitate to ask it, and see you in the next video. Welcome to this new video where we will talk about tail recursion. Okay, in previous videos we talked about the call stack and we said that it gives us the ability to go back to a recursive call and continue the remaining instructions. For example, in the factorial function, we are performing the recursive call, then we go back to the call to perform the multiplication and return the result. So we have to save a stack frame to be able to go back to it later. But what if the recursive call was the last thing to do in a call? In that case, we would have no more instructions to perform after the recursive call. In other words, we don't need to go back to it later. So we don't need to save a stack frame on the call stack, which means that we don't need extra space for the call stack, and this is what we call tail recursion. A function is tail recursive if the last thing it does is calling itself again, and when a function is tail recursive, the compiler will know it and will optimize the process by directly removing the stack frame after finishing that call. An example of a tail recursive function that we made is binary search, because as you can see, in recursive cases, the last thing the call does is returning the function again, so we don't need to go back to it. We can say that its space complexity is constant. It's not using extra space for the call stack. Okay, but the question is, can we turn a non-tail recursive function into a tail recursive function? The answer is yes, but not always. The idea to turn a non-tail recursive function into a tail recursive one is to use accumulators. By accumulator we mean a parameter that will have an initial value that will keep changing during the process until we reach the base case where it will be ready to be returned. Let me give you an example. We said that the factorial function that we made isn't tail recursive because we need to go back to the call and perform the multiplication. But we can turn it into a tail recursive function by using an accumulator whose initial value is 1. Then at each call, we replace arg by arg times n. In other words, at each value of n, we multiply arg by it, and that's how factorial works. We start with 1, then for each integer I between 1 and n, we multiply by I. And when we reach the base case, which is when n is 1, our accumulator will be containing the product of integers we pass through to reach 1. So it will be containing the factorial we're searching for. This is why we return it. Let's see how the process works with n equal to 5. With a non-tail recursive function, we would have fact5 is equal to 5 times fact4, and fact4 is 4 times fact3, and fact3 is 3 times fact2, and fact2 is 2 times fact1, and fact1 is 1, the base case, and now we keep backtracking while returning the product. 2 times 1 returns 2, then 3 times 2 returns 6, then 4 times 6 returns 24, then 5 times 24 returns 120, and we got 5 factorial. But with the tail recursive function, the call has two parameters, n and ac, the accumulator. In our example, n is 5, so n starts at 5 and ac at 1. Remember that at each call, n becomes n minus 1 and ac becomes ac times n, so here it returns fact4 5. Now this one returns fact3 20, which returns fact2 60, which returns fact1 120, and now n is equal to 1, so we reach the base case, we just return the accumulator. It actually contains the factorial we've been calculating during this process, 120. And you can see that we only had to save the actual call, not all of them, so our space complexity will be constant. Before moving to the next video where we will see more examples, you have to know 4 things. First one, as said earlier, not all recursive functions can be turned into tail recursive functions. An example of that is when the return statement depends on the value returned by the recursive call. In that case, we cannot predict the result, so we don't know what value will be returned. This is why we have to go back to that call to know what to return. Second thing, not all languages support tail call optimization. Some of them do, like Haskell and Scheme, but some of them don't, like Java. And if you're using a language that doesn't support TCO, the best alternative is to transform your tail recursive function into an iterative one that uses a loop. We will see it in the next point. Third thing to know is that a tail recursive function can be turned into an iterative function. I know that in a previous lecture I told you that every recursive function can be turned into an iterative one by using a stack if needed, but the difference is that with a tail recursive function we don't need a stack, so the conversion is pretty easy to do. For example, we have this factorial tail recursive function. We can turn it into an iterative one like this. The accumulator starts at 1, then while n is greater than 1, we multiply ac by n and we decrement n. After the loop, we return the accumulator, that's it. Fourth thing, the opposite of the previous one, is the fact that we can turn an iterative function that doesn't use a stack into a tail recursive function. For example, we have this iterative function that is replacing all occurrences of val1 by val2 in R, and we can turn it into a tail recursive function like this. And here we don't even need an accumulator because we are just traversing and replacing. We don't need to return a value. I hope that you understood tail recursion. See you in the next video to do more examples on it. Welcome to this new video where we will see some examples on tail recursion. The idea of this lecture is to give you some non-tail recursive functions, and the goal is to try to turn them into tail recursive ones, so please try to do so before watching the solution. The first example is an easy one. This is a recursive function that returns the sum of integers between 0 and n inclusive. Pause the video and try to turn it into a tail recursive function. For this one, we want to calculate the sum, so the idea is to use an accumulator that starts at 0, and at each call we add n to it, and when we reach the base case, in other words when n is 0, we return it. So in code, we would write if n is 0, we return ac, else return sum to n minus 1 ac plus n, that's it. If we call this function with n equal to 5, the initial call would be sum to n 5 0. Then it returns sum to n 4 5, which returns sum to n 3 9, which returns sum to n 2 12, which returns sum to n 1 14, which returns sum to n 0 15, and here n is 0, we return ac, which is 15. And the thing is that this 15 gets returned directly to the function that called the initial function call without passing from all the recursive calls we did. Second example, given two strictly positive integers a and b, we want to write the function that calculates a power b. And we can do it recursively because we know that a power b is equal to a times a power b minus 1. So we have our recursive case. We also know that any strictly positive integer power 0 gives 1, so we have our base case. And this is what the recursive function would look like. If b is 0, we return 1, else we return a times power a b minus 1. But as you can see, the recursive call isn't the last thing done in the function. We have to go back to it, perform the multiplication by a, and return. Now pause the video and try to turn it into a tail recursive function. Okay, let's see the solution. Here the base case returns 1, so the idea is to use an accumulator that starts at 1. And in the recursive case, we are multiplying the result returned by the recursive call by a. So in the tail recursive one, we will multiply arc by a, until we reach b equal to 0, where arc will contain the value of a power b, we return it. So in code, arc starts at 1, then if b is equal to 0, we return arc, else we return power a, b minus 1, arc times a. If we call this function with a equal to 3 and b equal to 5, then the initial function call would be pow 3, 5, 1. It returns pow 3, 4, 3, which returns pow 3, 3, 9, which returns pow 3, 2, 27, which returns pow 3, 1, 81, which returns pow 3, 0, 243. And here b is 0, so we return arc, which is equal to 243 in our case. It's the value of 3 power 5. Next example, getting the minimum value in an array. You're given an array R and you have to find the minimum recursively. The idea to find the minimum recursively is that the minimum of an array of n elements is the minimum between the first element of the array and the minimum among the n-1 remaining elements. And when we have no more remaining elements, the minimum is the infinity. We can implement this method by slicing the array again and again, but we've said that it's better to use an index I instead of always slicing. So we have an index I that starts at 0, and if I is equal to array's length, then we have no more remaining elements, so we return infinity. Else, we return the minimum between the actual element R of I and the minimum of this array when we start from I plus 1. But this function is non-tail recursive, because we first need to get the minimum value from remaining elements, then comparing it with R of I. So pause the video and try to write it in a tail recursive way. Okay, let's start. Here we are searching for the minimum, so we need an accumulator that keeps track of the minimum value, and at each call we replace arc by the min between arc and the actual value R of I. And when we reach the base case, which is when I is equal to R's length, we return arc. So in code, we add the parameter arc that starts at infinity, then if I is equal to length of R, we return arc, else we return getMin of R, I plus 1, and the minimum between arc and R of I. Let's see an example with the array 4, 5, 7, 2, 6. The initial function call is getMin R0 infinity. It returns getMin R1, 4. 4 because it's smaller than infinity, so it replaces the actual value of arc. And this one returns getMin R2, 4. 5 is not smaller than 4, so arc doesn't change. This one returns getMin R3, 4, which returns getMin R4, 2. Arc changed, so we found a new minimum. This one returns getMin R5, 2, and here I is equal to the length of R, so we return arc, which represents the minimum value in R. And as said earlier, we can turn a tail recursive function into a simple iterative function that doesn't need a stack, and it's the case here. Here's an iterative function to find the minimum in R. Next example, we want to print a binary tree by using the in-order traversal. The in-order traversal says that we print the left subtree, we print the node's value, and we print the right subtree. So in code, we would write this. Now you may tell me, here the recursive call is the last thing the function is doing, and you're right, but the problem is that here we have two function calls, and we are still doing things after the first recursive call, so this function is not tail recursive. Pause the video and try to turn it into one. In reality, we can't really turn it into a tail recursive function, because after traversing the left subtree, we have to go back to where we were before to be able to traverse the right subtree. This is why we need to keep the stack frame to be able to go back to it later. Does it mean that all the recursive functions that have two or more recursive calls can't be turned into a tail recursive function? No, and we will see it in the next example. Next example, getting the nth term of the Fibonacci sequence. We know that fib of 0 is 0, fib of 1 is 1, and fib of n is fib of n minus 1 plus fib of n minus 2. So here is the recursive function. Note that this recursive function isn't optimized, so it would be better to use memoization or tabulation. And you can see that it's not tail recursive because we need to go back to the call and calculate the sum, then return. Now pause the video and try to turn it into a tail recursive function. Okay, let's start. First of all, let's try to write the iterative function to calculate the nth term of the Fibonacci sequence. The idea is to use three variables, actual, prev, and prev. Actual represents the actual term un, prev represents the previous term un minus 1, and prev represents the before previous term un minus 2. At the beginning, prev represents u0, which is 0, prev represents u1, which is 1, and prev represents u2, which is u1 plus u0, which is 1. Now, if n is smaller than or equal to 1, we return n, else we have to use a for loop to calculate the nth term. The idea is that at each iteration, prev becomes prev becomes actual, and actual becomes prev plus prev. It's like we wrote un equal to un minus 1 plus un minus 2. After the loop, we return actual. You can see that we could solve our problem by using an iterative function that doesn't require a stack, so as said in the previous video, we can turn it into a tail recursive function by using actual, prev, and prev as extra parameters. So prev starts at 0, prev starts at 1, and actual starts at 1. Now, if n is smaller than or equal to 1, we directly return n. Else if n is 2, here we return actual, which is the accumulator we used to solve the Fibonacci term we're searching for. 2 because our for loop is starting at 2. Else, prev becomes prev becomes actual becomes prev plus prev, and we return fib n minus 1 prev actual. Let's see how it works with n equal to 7. The first call is fib 7 0 1 1. It returns fib 6 1 1 2, which returns fib 5 1 2 3, which returns fib 4 2 3 5, because 1 became 2, 2 became 3, and 3 became 3 plus 2, which is 5. This call returns fib 3 3 5 8, here 2 became 3, 3 became 5, and 5 became 5 plus 3, which is 8. Then this call returns fib 2 5 8 13, and here n is 2, so we reach the base case, we return actual, which holds the value 13. We've reached the end of this chapter. I hope that you understood tail recursion, ask questions if you didn't understand something, and see you in the next video. Welcome to this new video where we'll talk about double recursion. A double recursive function is a function where one of the arguments is a value returned from a recursive call. An example of that is the Ackermann function. It's defined as follows. It takes two positive integers m and n, then if m is 0, it returns m plus 1, else if n is 0, it returns acc m minus 1 1, else it returns acc of m minus 1 acc m n minus 1. You can see that we kinda have nested recursive call, it's double recursion. Okay, but how does this function work? This function works normally, it's just that we need to calculate the value of the inner recursive call, then we will be able to perform the outer one. Exercise, try to draw the recursion tree of ACK22. Please pause the video and try to do it. Okay, let's start. The first call is ACK22, and none of them is 0, so we execute the else. The first need the value of ACK of m n minus 1, which is ACK of 2 1. Same thing here, we need the value of ACK2 0. Here n is 0, so we return ACK m minus 1 1, which is ACK of 1 1 here. Now we first need the value of ACK of 1 0. We are in the case where m is 0, so we return ACK of 0 1. Now m is 0, so we reach the base case. We return m plus 1, which is 2. Here we return the value returned from the call, which is 2. Now we have the value of the inner call, so we can perform the outer call. It's ACK of 0 2. M is 0, base case, we return m plus 1, which is 3. Here we return the value of the outer call, so we return 3. Here again, we return 3. Now we have the value of the inner call. We can perform the outer call, which is ACK of 1 3. Now we need the value of ACK 1 2. For that we need the value of ACK 1 1. For that we need the value of ACK 1 0. Here n is 0, so we return ACK of 0 1. M is 0, so we return m plus 1, which is 2. Here again we return 2. Now the outer call, ACK of 0 2, it returns 3 because m is 0. Here we return the value of the outer call, which is 3. Now the outer call, awk of 03, it returns 4, which then gets returned by this call. Outer call now, awk of 04, it returns 5, which then gets returned by this call, then this one. Now we got the value of the inner call, we can perform the outer call, which is awk of 1, 5, and I'll just let the animation continue it. And you can see that we got the value 7. So in Bryof, in the recursive case, we first need to get the value of the inner call, then we can call the outer call. Note that double recursion is often confused with recursion with 2 recursive calls, which is not the same thing. Every double recursive function has 2 or more recursive calls, but not every function that has 2 or more recursive calls is double recursive. You also have to know that the Ackermann function is not primitive recursive. A primitive recursive function is basically a function that can be computed with a program that uses for loops only. In other words, how the upper bound of the number of iterations can be known before the execution. For example, the function that we use to solve ways to climb stairs is primitive recursive, because we know that it won't need more than m power n iterations. But for the Ackermann function, we can't know. We can write it iteratively, yes, but we need to use a while loop. We can't use a for loop because we don't know the upper bound of the number of iterations. All we know is that the function will stop at some point. We've reached the end of this short lecture about double recursion. I hope that you understood it. Ask questions if you didn't, and see you in the next video. Welcome to this new video where we will talk about how to think recursively. Even if it's the last chapter of this course, I'm sure that some students are still struggling with the concept of recursion. So in this video, I'll try to give you some keys to become more comfortable with recursion. The first key is understanding. You need to understand the concepts that are related to recursion, the ones we've seen during this course. So you need to know what is recursion, what is a base case, what is a recursive case, the call stack, the recursion tree, etc. And most importantly, you need to understand how does the recursive process work, how does a function call itself, what happens when we have multiple calls, where do the recursive calls get stored, how to visualize the recursive process, and all that stuff. Understanding is very important because if you don't know how recursion works, even if you read the solution of a problem, you'll struggle to understand the logic behind it, because you don't know how does it work exactly. So if you still don't fully understand the concepts we've seen during this course, my suggestion is to ask me some questions or to make some researches. Second key, dividing the problem into subproblems. When you start thinking about how to solve a problem recursively, identify the input and try to see if you can solve the problem by solving smaller instances of the same problem, either by decreasing the input or by dividing it. Because recursion is all about calling the same function with a smaller input until reaching a point where the input is so small that we can directly give the answer. Like factorial 1, we know that it's 1. And when thinking about how to solve a problem recursively, you have two ways of thinking. You have the top-down thinking, where you start from the initial input and you keep thinking about a way to divide it more and more until you reach the base case, the case whose the answer is known. Or you have the bottom-up way of thinking. You start by finding the easiest possible situation, which is the base case, then you try to figure out a way to solve bigger and bigger problems starting from that base case, as we did in dynamic programming. In Bryof, you can either think about the recursive case then move to the base case, or the opposite, thinking about the base case then moving to the recursive case. Try to find the method you prefer, it depends on your way of thinking. Try to find the one that is easier for you. Third key, trust the recursive process. This one is very important. One of the things that are confusing when writing a recursive function is that when you call the function again, you're using a function that you're still defining, so it's kinda weird. This is why you start having doubts about if things will go right when you'll use this function later, because you don't trust the recursive process. So the solution for that is that when writing a recursive function, assume that the function works. Don't overthink about it. Try to work as if the function you're using to solve some problems is another one that works perfectly. Don't think about if things will go right because you're gonna use the function you're defining. So if your function works, then the recursive process will work. This means that your goal is to figure out base cases and recursive cases only. We don't care about what's gonna happen in the middle. Just assume that things will work. Trust the recursive process. Then, if when using your function later something wrong happens, it means that something isn't right in your function, and this is why we need the fourth key, visualizing the process. When you want to debug a recursive function, the best thing to do is to visualize what's happening. You can visualize it mentally, but it's kinda hard to maintain all the recursive calls and their relations in your head. So it's better to draw the recursion tree on a paper or by adding some code as explained in a previous lecture. Then once you got the recursion tree, you can compare it to the expected one and find the issues. Fifth and last key, practicing. Even if you know all the theory behind recursion, you can do nothing without practicing. Practicing will develop your patterns, which means that you'll become more and more quickly when solving a recursive problem. Practicing will also show you how can we start thinking about a recursive solution for a problem, because when facing a problem, sometimes we don't know from where to start, or we can't perceive a way for how to divide the problem into subproblems. So by checking more and more solutions to recursive problems, you'll start understanding how to do so. We reached the end of this course. I hope that you enjoyed it. If it's the case, you can check the other courses of Inside Code in the description. See you in another video.